Okay. There's that. Mm. Oh, nice, nice. I like it. Hello, hello, hello. Excellent. Hello, hello. Be ready.
Is my phone gonna arrive?
Hello, hello. Good to see you. Good to see you. I'm just waiting as everybody comes in. Hello, hello, hello. Very good to see you.
Oh.
Hello, hello. Good to see you. Hello. Welcome. Welcome. Be right there. Okay, hello, hello, hello. We have a lot of people again. This is great. This is great. Oh, more people waiting. Sorry. We'll start in a second. Um, Thank you all for being so on time. So on time. I'm stalling slightly to let everybody in. And also today, I know, yeah, we have another full room, so to speak. I know some of you are here, were not here yesterday, I'm sure because of me, because you didn't know where to go. And I apologize for that. If you weren't here yesterday for whatever reason, you don't owe me an apology. You just need stuff to get caught up. So the main thing for anybody who wasn't here yesterday, I will get to know you, I'll get to know everybody, hopefully. But if you weren't here yesterday, the most important thing, I guess, is a syllabus and stuff like that. But all that stuff is in Google Classroom. So if you weren't here yesterday, you have any familiarity at all with Google Classroom from high school or from college, then we use it, then good. And then you'll need to join our Google Classroom with the code, which you might have seen, hopefully you saw in the waiting room. Anybody who wasn't here yesterday, if I don't resolve this by the end of today's class, if you can hang out for 2 minutes so that I can give you the code, if someone else doesn't give it to you, then all the material will be there and you're not too far behind or anything. If you're not at all familiar with Google Classroom, you may need a little help with that today in the class, but again, just hang out for 2 minutes at the end and I'll catch you up. So this is all by way of saying, again, hopefully we're all, wow. Yeah, hopefully we're all going to learn a ton of physics in a very surreal but calm and unstressful way as much as possible. And we should all do very well in physics, even if we weren't here yesterday, blah, 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 blah. Okay, I think everybody's, we're about to start. We now have, we have like 48 people, almost. It's quite a group. All right, and we are, our first item of business is, I'm assuming you can all see and hear me right now. Can I get like an electronic show of hands that I'm coming through? And there's more people in the way. Oh, thank you, totally appreciate it. Awesome, great, thank you. If by some miracle, crazy bad circumstance you don't end up with an A in physics, then I give you an A in Zoom skills. Really, this is awesome. All right, so everybody can hear me. That's good. More people. We really have a full room. All right. So we really should get started. Oh my God. Excuse me. Right. Let me verify this too. Can someone just make a noise so I can make sure that at least when you turn your microphone on, I can hear you? Because right now I'm just hearing my own.
Can you hear me?
Yeah. Thank you. Excellent. Thank you. Okay.
I have a question anyways, Professor.
Yes.
Can I ask something?
No, please. Yes.
Professor,
Yes.
I finished the homework and I was trying to change it to a PDF and upload it, and it was having a problem with that. So I just uploaded it as pictures. I don't know if that's okay or not.
It's definitely okay that you just asked that. That's exactly the kind of thing I do want to deal with right now. Yes, I mean, the answer unfortunately is slightly long. I mean, the short answer is I'd prefer not that. It is okay that you did it today. It is definitely okay that you did it today. In the long run, yeah, okay. But I'm going to part of today is just, we're going to work through exactly those kind of technical issues for everybody so that there's no problem. And that is, in fact, our first item of business, other than me saying I would like to take any, well, no, maybe I shouldn't. Yeah, the very first thing we're all going to do together today, and again, this is obviously clear to anybody who was here yesterday, but even if you weren't, I think this will be clear in a minute. There was homework last night. Everybody was asked to try it and all that. And then, yes, I asked everybody last night to try to compile all their homework into one PDF, which I know is super easy for some people and super not, or for some systems and super not for other systems. Our first item of business is we're going to make sure that everybody in the room today goes through the exercise of changing something into a PDF and submitting it properly to the homework portal. We're all going to do that, even if it takes a little time and bores a person or two, because, well, for the obvious reason, I guess, but I want to make this, even those of you who last night even those of you who don't know what the homework was. So how could you possibly submit it? That's not going to be held against you. It's not, and any of you who did the homework but did it horribly or whatever, not going to be held against you. The first item of business is for us all to make sure we don't let all these technical things get in our way. So what I'm going to say to all the people that haven't had a chance to do homework yet, for whatever reason, if you even just write your name down on some piece of paper somewhere, like your name, your email address that you're going to use for this class, and just some sentence like a fuller draft of this homework will be submitted later, just anything like that, that will serve as your homework today. That will serve as the thing you're going to put in. And you will, please, because our first goal today is that we're going to make sure that every single person has had the experience of successfully submitting something the way I want, and then we're going to go over the homework and stuff like that. And I'm telling all of you right now, whether you did it awesomely, whether you didn't do it at all, whatever, everybody can resubmit this homework without penalty. Like everybody's going to just keep resubmitting this file until it does get a perfect score, which it will. So like basically everybody's job is to not move on in this class. So my job, I'm sorry, is to not move on in this class until everybody's gotten 100 on the first homework. I don't really mean I'm not going to move on. Of course I'm going to move on, but I'm saying you have as long as you want, as long as you need to get this right, but it will be very hard to get any other ones right until you do. So, that said, yeah, and if you already submitted, oh yes, right, thank you. Yes. Great. Oh, great questions. Thank you. Oh, I'm looking at all these chats now. First of all, I was totally hoping that this would happen, that you all are helping each other, like concisely do this, like the PDF stuff. Great. I echo these suggestions. I will make further suggestions if necessary. But yes, if you, oh wait, sorry. Right. Okay, you're all saying correct things. For this very first homework is what I'm talking about right now. For this very first homework, at first I did say don't hand it in. I said not to, that's true. But if you did already turn it in, you're still not, don't worry, that's fine. The truth is I didn't even know if I could get the Google Classroom portal working in time to make it fair for you to do that. So I'm glad if anybody already turned it in, great. That means you're just a step ahead and you're good. I will say this to those people who have already handed in, if you hand it in as one PDF, and you're pretty confident of it, great, then you can chill or you can help other people in a minute or blah. But when we start going over it now, today, when we start going over it, those of you who already turned it in, you can still return it in if I start saying things that make you realize, oh, I did that one wrong, or I could do that one better, or I get it better now, whatever. You can return in this thing as many times as you need to get 100. And so that's everybody. We're obviously, at a certain point, I'll go on with my teaching and all of that, but I do want everybody to see exactly what it is I'm asking for and to know that they know that, so there's no anxiety. So again, if you already turned it in, you can still turn in it again if you think you could turn in a better one. And on this, here's now, how does this apply to all the rest of the homeworks? Someone just asked, good point. In a way, this will always be true, but just squeezed in time. What I mean by that is this: on this homework, not only can you, but you should resubmit it again until you get 100. So that you can see how easy it is to get 100, because you'll get 100 on this homework even if you get some answers wrong. I want you to see how it's graded and how you get credit for completion, not correctness. So on this one, everybody, no matter how many times it takes, they should keep resubmitting it until they get 100%, which is actually technically called a 50. I'll explain that. But for all the future homeworks, believe it or not, the policy is still true. On any future homework, you can resubmit as you think your responses to the homework are getting better. You can always resubmit. You can also, you can submit late, like to a point. As long as the portal exists for any homework throughout the semester, as long as you see a place to put a homework that you have, you can put it in. Can I possibly at a certain point give you fewer points than otherwise You know, if it's a little bit late, sure, like I do reserve that right. If I think, in other words, if I think by the time you returned in and we've gone over it a million times and it's all clear on the board and it's not that much of a credit to you, then I may, you know, dock some points in acknowledgement of that. But it will always definitely be more worth your while to submit something late than not to submit it at all, as long as the portal's there. And it's definitely worth your while even to submit things, even after we've gone over them, as long as you make it super clear that that's what's going on, that like you're using class to your benefit, like, you know, then God bless. Just be clear about that. So yes, from, and I'll keep saying, as long as these are such good questions, I'll say one more thing about this and then we'll do it. The way the homework works in the grading and all of that is all explained in the syllabus. Hopefully you did get a copy of the syllabus in the Google Classroom if you're signed up, but that it's all there, but that doesn't mean I'm now not going to address it. It's all there so you can go back and refer and stuff, and because it's a contractual agreement and blah, blah, blah. But the actual facts of grading that are most important are these. Every homework you do is points on your average. The truth of the matter is homework is great. The way homework counts is actually more like what you would consider extra credit than anything else. Here's literally, and I know this is super boring, but also super important to everybody. So stop me if I'm being unclear, but this is really how the class works. We have a final exam, we have a midterm exam, we might have a second midterm exam, but frankly, it's super unlikely in a 5-week Zoom class. So we have a midterm exam and a final exam, and we'll talk about those separately, but they are, you know, they're averaged in a customary arithmetic mean way. Like, you know, if you got 100 on one, you got a 90 on the other, then like your average is a 95. But then your final grade in lab also then counts almost, I mean, because technically it counts 35% or whatever it says in the syllabus, that almost effectively means that it's just another exam. Like all of what you do in lab, in effect, amounts to another exam grade when all is said and done. So you take these 3 grades, I take these 3 grades at the end of the semester, right? You're like your 2 exam grades, your lab grade. Generous things can happen on either of those 2 exams, like there could be extra credits and blah, 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 but just assume when all that's out of the wash, you've got these 3 grades, they get averaged together, and then here's the key to everybody, how this relates to homework. That average of your 3 exam grades is your like pre-grade. It's your testing average, whatever. It's your unadorned average. With every homework you do, you get points generally out of 50, right? So they say this first homework here is worth 50 points. You'll get a 50 on it. That 50 goes in my book as a 50. I mean, you know, as 50 points. Then you do another homework, that's another 50 points. Okay, that's 100 total points. At the end of the semester, everybody has this huge pile of homework points. What we do at the end of the semester, when we're averaging the grades, is everybody has this big pile of homework points that they did. And we come up with one number, which is the dividing number, you could say, the scaling number, the weighting number, you know, for each semester. It's a new number every semester, but it's the same number for all students, of course. So say that we come up, and I'll tell you how we come up with the number in a minute, but we come up with some number like 7. And if the number is 7, that means your entire homework pile of points gets divided by 7. And whatever that answer is literally the amount of points that we will add to your average. So I mean, literally, if you've accumulated 70 homework points and we decide that the number is 7 that semester, then we divide 70 by 7, and that's 10 points that gets added to your test average to make your actual final average in the class. Is that a realistic example? It's a realistic example for a good student. Like 10 points is possible. Typically, you'll end up with like 8 or 7 points that you got just from doing homework. People have gotten like 14 points before. It is definitely a grade changing amount, though, is what I'm saying. Like all the homework you do gets added onto your average and will absolutely change a B+ to an A- or an A, or a C- to a C+, blah, blah, blah. Like it's designed to make that big of a difference. And the final word on this, at the risk of talking too long or too fast, is that when I say it's a pile of points, I have to keep saying that because I have to really make clear on this homework, on every homework that you do, say the homework is worth 50 points, which they generally are. If you get a 40 on that homework, it doesn't mean that you got a 40 out of 50. Like, it's not like getting an 80%. You're not getting docked. You did 20 in any way. It's just that you got 40 extra points to add to your homework pile points, whereas maybe you could have gotten 50, or maybe your friend got 50 or something, or maybe if you have time and you want to resubmit, maybe you will now bring it up to a 48 or 50 or something. But you're never being, and again, those numbers that we come up with are based on how you do the homework, not necessarily on correct answers. So the point I'm really trying to make is every bit of homework you get is meant to be a reward that inflates your average, and is meant to do so even if you get wrong answers. And it's also meant to, it's also understood that here and there you might miss a homework or this or that. And even though technically we have the right to give you a 0 on that, we never do. It's all about just viewing every bit of homework as a positive helpfulness to your grade. And so it's really important that there be nothing in your way to do that. Like, it just requires knowing how to submit it properly. That's why we're going to do it all today. I think we should get started. I feel like, and on that line, and stop me if I'm not making sense. What I'm ultimately saying is, and by the way, please, as you get to know each other, I know there's people in this room that took 203 at John Jay. And there's a lot of people who didn't. As you get to know each other better, I encourage the people who didn't go take physics at John Jay to privately talk to other people, like not in front of me, and ask them if they want to share. I think they'll say that they were surprised that their grade was a lot higher than they thought it was going to be at the end of the semester if they did a lot of homework. It usually works that way, that it makes a surprisingly high difference. A surprisingly large difference. So I want to add to that a new thing now that I'm implementing because of Zoom and all of that, or viruses. I'm also going to open a portal today for an extra credit homework portal, which will be for, at any moment, anybody who, and I'll give you examples as we go, I'll show you this. At any moment, if any one of you comes up with some little way of solving a problem, like even if you just draw out a screen recording of solving a problem that you're proud of, that you know well. What I'm trying to say is, anybody who submits some kind of demonstration, something that might be at all fun or helpful to anybody to learn how to do anything in this class, like anything that you've mastered that you can somehow try to capture in a video, or a solve through, or a physical demonstration at home that you make a video, anything that would be YouTubeable, so to speak. If you make something like that, that just shows that you've worked through and you understand something now and could possibly be helpful to other people to understand that will totally count as another homework you did. That could be another 50 points. And if it's large enough, I'll be willing to double count one or something. You'll see examples as we go through of things that students have done in the past that I'm talking about. Largely every time I'm starting to stutter or try to explain something difficult, I'll often refer you to videos that either I've made or past students have made that are helpful to the concept now. So I'm just saying, if you contribute to the arsenal of that in any way, that's extra credit. And it doesn't have to be video or computer at all. Like a quick example is, there's a lot of, if you ever type into YouTube, Rube Goldberg machine, I'll type it right now, actually, so you can see. A lot of you probably have a long time ago, but maybe some of you haven't. If you ever type in something like this into YouTube, basically that's the phrase. You'll see all these crazy contraptions that are awesome and hilarious and fun to watch, that definitely demonstrate energy conservation, among other things. And they're great. And they're I don't want to get, they're wacky. Or if you type in this, for example, on your own time, or right now if you're bored, if you know everything I'm saying and you just want a diversion, I highly recommend typing that into YouTube. It's an example of one of those. It's this long, incredibly bizarre machine that ends up just turning a page of a book. It's hilarious. And they're fun to make at home while we're all in quarantine. So if you come up with any way to help anybody out there in quarantine land who's like climbing the walls and needs a physics concept demonstrated, and even if that person's you, then if you do that and submit a link to it to me or somehow submit it to me, that's definitely extra credit. And again, I'll show you examples as we go on of things. And I'll also give something about myself away right now. A perfect example too would be, and this will appeal to some people and definitely not to others, but like if we're about to study pendulums, right? If for example, you made a Mario Maker course or out of those pendulum gadgets that they have in some incarnations of Mario 64, or you made like a Minecraft Rube Goldberg machine, which there are all over the web. In other words, if you do a video game thing, great, I'm all for it. Anything that can turn physics into something cute and fun and tolerable in these crazy times is extra credit for sure. And it could include just writing a story or make a picture, blah, blah, blah. I'm gonna stop talking about that now, but there's tons of ways to get an A in this class. And there's very few ways to do very badly in this class. You have to really, really, really check out and leave me no choice to do badly, I hope. That said, let's talk about this homework. Raise your hand if you do have a PDF like ready to submit. Great, great. And that means people are still paying attention after that long. So great, great, great. Awesome, awesome. Raise your, thank you. And put your, awesome, okay. And put your hands down now, please. Great, thank you. Raise your hand if you actively have something, but it's not a PDF yet. Like, raise your hand if you're stuck at that stage of how do I turn something into a PDF. There are a couple people. Okay, and I do need it. I know this sounds crazy, but every homework you submit, I do need to be one PDF file for a number of reasons that include my ability to correct it and get it back to you fast. It will just hold up the process if it's not. So can I ask right now to pause again, like you did a minute ago, could people in the chat sort of, well, my best recommendation for turning things into a PDF, I'll say this. Because I want it to be clear to everybody, I want you to do the homework however you do it, like pen and paper, whatever you're used to. But once you've scrawled out answers and work on a piece of paper, then we got to get into the computer. I think the easiest way, if you don't know how to turn pictures into a PDF, or you don't have a scanner or whatever, I think the easiest way, if you have a bunch of pictures that you want to turn into a PDF, is just start a new, fresh Microsoft Word document, and insert the pictures into a Microsoft Word document. Just insert one picture per page of a new Word document. And then once it looks the way you want it to look, then go to print. And instead of printing it to a printer, print as PDF. I'm not saying that's the best way or the coolest way, but I think it's a very straightforward way for a lot of people. I hope it helps. So if you have pictures sitting there, please, open up a Word document, put them in, turn into PDF. And I do kind of mean right now, what we all want right now, and of course, we're not going to take all class on this, but once everybody has some kind of PDF, and maybe even if right now it's fake, if it's just a placeholder, fine. Once you have a PDF, you do want to go open up your Google Classroom app, whatever way, and enter that PDF as your assignment, like literally right now. Again, if it actually is your assignment and you actually did all the questions and it's all clear and stuff, you're going to get 100 for this right now. But I am going to see what you did, but I'm telling everybody, the first thing I'm looking for is I want to see that everybody can turn something in. So please right now, even if you have a fake PDF or something, please take a minute to join Google Classroom and submit something. And I'm going to, and even if you submit again something later, it will, this is what people were asking before. For all homeworks, every resubmission is fine. Every time you resubmit something, it's fine. Do the old ones stay there? Yes, I think it's don't unsubmit the old ones. You should leave them there, but I will always just first look at the most recent thing you put in. I will assume that is like your best copy or whatever, and I won't hold against. And if I see 5 old copies there, I'm just going to think, well, the person's working hard in this class. Okay, so don't try to undo history. But please, everybody, right now, go to Google Classroom. I'll write the code down again in the chat, and try to submit this. And I'm going to watch and see that we have a bunch in. And again, if you've already done it, go take 5. If we use it outside. Oh, great question. Oh yeah, and they have apps, scanning apps, great, great, great. But someone, oh, sorry. Does the topic, all right. So everybody please try to do this. I'm going to try to answer questions out loud right now while you're doing it. Does the topic need to be related to what? That's a great question. Erica B's, oh, sorry. Sorry. I'll move on for a minute. They have apps where you can, if you used, wait, this is a very important and good question, and I might be on this one. If you ever use outside sources in any way for your homework, which you should definitely, I don't mean to say that you have to tell me that. Whatever sources you use to do your homework, whether it's online, whether it's your sister, like your husband, whatever, it's not that I need you to cite them. It's not that at all. It's that it's on your honor to only write down things once you understand those things. So I want you to use whatever resources you can to help you understand things. And I don't need you to tell me who they are or whatever, because this is not research citation. But I'm just saying what it means to get help is that you go to your sister and your sister says, oh no, this is how you do it, blah, 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 blah. And you're like, oh, and then she's like, do you get it now? And you're like, yes, thank you. Well, that's great. And then go write all that crap down because now you get it. So now you own it. Like she didn't make that up either, right? You don't have to make up ideas for them to be right. And that's all cool. And then you don't have to cite that. You don't have to tell me that your sister is involved or whatever. Just keep practicing with her and make sure she's not there when you take the exam. But if your sister, hypothetical sister, says like, oh, well, you do F equals MA and then you plug in 7 for A, like that's what you do. And you're like, okay. And you write down what she said, but you don't get it. That's what you shouldn't do, like ever, for your own sake. Don't write crap down that you don't understand. Understand it and then write it down. Now, how am I going to know if you write down things you don't understand? There's 2 answers to that. 1, believe me, I do. 2, I don't care. I mean, I'm not gonna look for that in homework. That's on you, and it's between you and your conscience. But it's very good advice that you should follow, that you just get in the habit of considering the whole world your intellectual oyster of help and research. That's what the world is for, but just use the world to help you. Don't use the world to help you cheat, because duh. So yes, if you used outside source, did I misunderstand that question? Wait, Mariah?
No, that's what I was asking.
Oh, totally. Okay, great. Thank you. Awesome. Okay, and I don't know how to say it. Oh, so now how to submit a new document to Google Classroom, someone seems to be asking. Again, this assumes that you're already in the classroom, which some people might not be, but if you're in there, then actually, you know what? I'm a teacher, not a student, so I'm not sure I know. Could someone else answer Jessica's question? Has anybody? Well, I'll see. I assume someone has already. Someone told me they already successfully submitted. So could someone? Wait. Yeah. Wait.
Thank you.
Wait. Sorry. What?
I think I got it. Thank you.
Oh, great. Okay. Thank you. And then then on Grace's. Yeah. There you go, Gabby. Thank you, Gabby. That's totally helpful. That's what I should have said if I were helpful. Then Grace's comment to everybody. Yes. She is right. Configuration wise or technology wise, you can unsubmit a homework. That's one of the few settings there that I actually don't quite like. And I can't remember if I've decided, I might change that if I can. But what I agree, you can unsubmit. I'm sort of asking everybody not to. I think, again, I'll never know or care. How do I know if you unsubmit? I don't think I'll know. And I don't have time to actively look to get people in trouble. So if you do unsubmit, okay, I'm just saying unsubmitting is like obliterating and erasing things in the middle of an exam, which science students do all the time. And it's dumb. Like every bit of work you ever do, you should not obliterate from the universe, because first of all, I promise you'll get credit in this class. The fact it shows that you did work, and that's just a good thing. Like if I go to look at your homework and I know I already said this, but if I see like 6 submissions there, the first 2 could be so wrong that you think you're so embarrassed by how wrong they are, but you shouldn't be, because how psyched and impressed am I that you tried again 6 times? Like that's number 1. Number 2, I'm not going to look. I don't have time to look at the first stuff if you don't want me to. I'm going to look at your best stuff. So you don't have to be. And number 3, really, here's the most important thing in physics is if you ever once realize that that you could ever be wrong in physics and it makes you a little nervous or trepidatious, because like you can, if you've ever noticed that you could ever make a mistake in physics, then please join me in recognizing that that also means you can make a mistake about thinking you made a mistake. And this gets people on exams all the time. Like if you're working and I will get more into this, but if you're working on something on an exam and then you get someone, you're like, oh crap, like all that was supposed to be cosine, not sine, or something. There are people that will get so upset or freaked at themselves that they'll then spend time like making sure to white out their work so impressively that I could never imagine that mistake. But then they don't have time to put the right stuff down, or then it turns out that all was right, or it was more right than they thought, which it usually is. So please just consider anything you do like good. It should stay in the universe. Don't unsubmit. It's a bad idea for you, but I won't. But if you do, I won't know. All right, that's that. Yeah, it doesn't let you. Wait. Oh. Oh. This is a good class, right? Yes, good point. All right, I'm reading these. Yes, I now see what you right. On what Ayeta just said to everybody. Now I realize why someone said I can unsubmit. You're right. It doesn't let you resubmit until you unsubmit. That's true. That makes things difficult. Ideally you do what Ayeta just said, but I'll also say this. At any time we're doing homeworks or practice exams or something, if at any time it seems clear that people definitely need revision space and stuff, you can just remind me like, Yaverbaum, we need to do this again. Can you just open up an assignment portal for like take 2 on that homework? And I will, if you know what I mean. Like I could just set up a new portal if you just tell me, right. And then there's also that, what you're saying. Okay, I feel like it's better. Oh yeah. Oh my God, where are all you people from? Yeah, what Grace said, I couldn't agree more. It is better. It really is. It's better to use pen than pencil often in physics. It really is. I mean, a whole other, and I have a sheet on all the stuff I'll put into. I have a like tips and tricks of these kinds. And I know no one signed up for this class to sit here and learn how to do school for 3 weeks. So we'll move on. But no, all that's right. And there'll be less and less of this talk as we go. I just want you to know this general attitude that everybody seems to be conveying in the room and that I'm trying to convey is the right attitude. Like, yeah, let's just like have as much, let's like, move on. All right, let me see how many people have put in a homework. And if it's a lot, then we really can move on. Hold on a second. But keep these, if anybody has a question, well, I just see. All right, so we've got, so far in this class, there are, just so you know, there's 48 people in this class, technically. 44 people have gotten onto Google Classroom, which I find very impressive, appreciate. I understand 4 people still need to, probably because, and we'll work that at the end in the last 2 minutes. Now, as far as homework, we've got, wow. All right, 34 of you have turned it in. I really appreciate it. There are 10 people, which really means 14. Wow. So what I'm going to do is, nice. Someone used latex to type. All right, I'm outclassed. I'm walking away. Someone's using latex in this class, and I mean that as a math thing. Not, I don't mean that's how they're making their rubber gloves. Yes, as a teacher, I can see the submission history. I'm urging everybody to believe that that is a good thing for you. The more I see from you, just the better. And I'm really lazy. I'm not going to look into details that you don't want me to look into. I've got enough details I have to look at. What is that? Oh, latex. Well, talk amongst yourselves about that. Yes, if you like typing out homework and stuff, by all means do, but I don't want anybody to think that is not required. Your handwriting is totally fine as long as your handwriting gets electronically to me. So I'm going to walk away for a second because I want you, there's like 10 people who still haven't submitted it. I want you guys to help each other get those 10 people to submit just technologically. I'm going to walk away so no one has any embarrassment in front of me, but can you please talk amongst yourselves for 3 minutes to try to urge to see whatever issues are holding people. And if it's unsolvable now, then when I walk back in 3 minutes, you'll tell me that. But I'm going to walk away. Let's get all those homeworks.
Wait, what? He's basically saying for us to like help whoever didn't submit their homework already if they don't know how to do PDF or if they don't know how to work Google Classroom.
All right.
When I upload my thing, it says server rejected.
I've never seen that before, so I don't know how to help that.
All right.
It just says server rejected.
Yeah.
Would I get an Orgo? Bro, of course I got an A. Finesse the shit out of that class, yo.
I mean, is everyone like signed up for Google Classroom?
Yeah, that's the first step. Sign up for Google Classroom.
Yeah, and then it's pretty easy after that. You kind of just hit submit on the thing. If you like download the app or something, then you can scan it, or even if you want to take pictures, you can save it and turn it into a PDF through Word.
The PDF app was asking me, the PDF scanner was asking me to pay $50 for a year.
Hell no. All right, so
Kind of free.
Not
all
free.
right,
Is there a free app? Does anybody know a free app? 'Cause, like,
if you're on
I'd use
Android,
Cam Scanner.
if you're
that's
on
the one that I was
Android,
using. Is it this one? Okay, I'm gonna just show everybody. Is it the last one right over here? Do you guys see it? Does anybody see it?
Yeah, that's the one I use. Why, they're charging you? You don't
They're
have to
charging
pay
me
to use it.
$50, yo. Like,
Nah, you don't gotta pay to use it.
look. Hold
That's
up.
wild. I was gonna say I literally just went online, found a website that converted my JPEGs to a PDF for free, and just literally use that.
The other option is what you can do is get Google Docs for your phone. You can go on a Google Docs on your phone, and then you can literally just put the pictures into the document like directly, and then just go on your computer and then download it as a PDF on your computer.
Thank you. He said he's back.
Yes, I am back. Yes, thank you.
Okay.
Totally, not trying to eavesdrop or anything, but I did hear a sigh. I know this is complete. We're doing all this now so that hopefully it's never annoying again after now. I know all these particularities. I know they're annoying, but hopefully, if it seems like people are making progress, I think I've got most of them. Again, if you still haven't submitted it, just hang out in the last 2 minutes of class or whatever, or someone can warn me to end 5 minutes early, and we'll straighten it out. I think this is only annoying the first time and then not after that. Okay, so I'm gonna move on if that's okay with it seems like you guys are making yes, can I move so we can actually do some physics? But again, if nothing else, you can see by how much time we just spent on this, as boring as it is, it's meant to show you that's how much of a grade difference homework submission could make. So I think it's worth all of our while, but all right. Let's actually start talking about this homework now. And again, we're going to try to put it up. I'm going to do this on the screen. Those of you who still don't have Google Classroom, I just try to follow what we're doing on the screen. But we're going over it now. We're going over it on it. What's my point? We're going over it. That means we're learning how to do it better. So it doesn't mean this material's done when we're finished going over it now. In fact, we need it for the rest of this. I'm going to shut up. All right, let's go over it. All right, we got a mass on a spring, a thing on a spring, just like you had in lab. Next page, right? And it looks something like this. And by the way, I'm assuming, so we have something like this, right? Although maybe it's oriented the other way. Actually, it's probably oriented the other way. I apologize. We have a mass like this, and it's on a spring whose spring constant is, you'll have to tell me that, 200?
200.
200.
Thank you very much, great. And that's a sneaky way of finding out two people that did do the homework, thank you. Yes, okay, the K is 200. The mass is like
0.3 kilograms.
Awesome, thank you. And and we're going to call sorry. First of all, I am assuming everybody can see this whiteboard. So, I mean, this blackboard, is that correct? Like you can all see the screen, right?
Yeah.
Okay. So, and this, I believe, is the setup, right? And so in theory, this is old material from classical mechanics, i.e. from physics 1. But it's not just, this is not meant as, anyway, it's old material, but it's the first ingredient from which we build the new material. That is, this is a thingy thing from which we are going to build and mathematically construct the unthingy things that exist in the universe, most particularly waves. Like we're going to build a wave out of simple harmonic oscillators. This is a simple harmonic oscillator. That's the reason we're starting with it. One thing about notation, you'll notice, just the way I'm diagramming this right now, you'll notice I write x triple equals sign 0. And then I wrote x trip somewhere else. I wrote x triple equals sign x naught. And then under that, x double equals sign positive 15 meters. That's a piece of notation that some of you might be familiar with and might not. And I think it's a crucial piece of notation that I use all the time, the triple equal sign versus double equal sign. So before going, let me make that clear. Right, from now on in this class and in life, triple equal sign means
Equals.
so, yeah, well, of course it means equal, but I mean equal. Okay, a triple equal sign means equal by definition, which really then means equal always, necessarily equal. Like there would be a contradiction somewhere in the universe if the two things being discussed were not equal. Right, so put another way, as opposed to double equal sign, which means equal by condition or circumstance or discovery, etc. In other words, to say two things are double equal means it turns out in the world after we looked at things, after we observed, or after we did some computations or blah, 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 it turns out to be the case that this equals that. But that could mean that it could have been other ways. Whereas a triple equal sign means this must equal that, and there's no other coherent way for anything to be. And it might not sound like that makes a difference, but it really does make a difference, because basically the only way we ever get from not knowing something to knowing something in science, in my opinion, there's only two ways ever to move from unknown to known, and they are either by sensory observation, like input from the five senses, evidence, data, right, or by definition, analysis, mathematical computation. In other words, everything is either true we discover the truth of everything either by definition or by sensory observation. And there's huge advantages and disadvantages of both. But the main thing is it makes all the difference in the world knowing which one you're dealing with at any given moment. And I feel like that gets conflated all the time. And one reason people are confused all the time. So what I'm saying here in this diagram is from now on, the position that is the equilibrium position for some spring, like the place where a spring would be if left to its own devices, if you just leave a spring alone, the length to which it would just sit extended, we call that equilibrium position, and we'll call wherever that place is, wherever the end of the spring is under such conditions, we're going to call that 0. Like it's triple equal sign, because I'm saying from now on by declaration, the equilibrium position of a spring, that is the end point of the spring. Assume this orange stuff here is like a wall. So one end of the spring is rigidly attached to a wall at all times. The other end of the spring, we watch as it moves from one position to another, and we stick a mass on it so that we can really focus on where that end is at any given moment. That end of the spring, when it's at a relaxed place, we call it 0. We call it 0. And then any extension of the spring gets measured relative to that. So when this problem began, the very initial position of the spring happened to be 0.15 meters away from zero. Okay, so we called it 0.15. What I'm saying there though is,
A quick question about the diagram that's in this PDF. The
yes.
dotted line that goes through the block, is that 0.0 or is that 0.15?
Yeah, actually, you're right. Since I'm not, maybe I wrote it. Does the diagram, because I'm actually not looking at it right now. In the diagram, is there only that 0.15 designated? Is the zero drawn anywhere in the diagram?
It says they have two arrows going between the dotted point and the y-axis. And then the dotted point is the one that's going through the box. So would that sort of be a difference?
Sorry. So, okay. So yeah, you're right. So I guess I did it the other way around. And that's a good point. Hold on a second. Good point. It means, wait a second. It does mean that I guess I did it the other way around in the diagram. It changes things slightly. Hold on. That's a good point. I'm going to make that clear right now. Wait a second. I think you're saying this, something like, I think you're saying that the dotted line, the dotted line does or does not go through.
It does go through.
Does go through. Okay.
Access is to the left of it.
So, okay, I see what you're saying. All right. What the difference then, the difference in the way I just drew it and the diagram itself is it just happens, we're saying the same thing in both diagrams. I want to say for all time that wherever the equilibrium position of a spring is, we will call zero. And wherever a mass happens to start oscillating, we'll call x naught. And it may be the case that in that diagram, I was taking a picture in my mind when the thing had already, I was either right here when I was drawing, I was taking a picture in my mind when the object happened to already be at that position of 15. But in the picture you're looking at, maybe right at that moment, the mass happens to be at the equilibrium, or the other way around. Like those dotted lines won't change anything in what we're doing in the calculation. I think what the ambiguity that you're pointing out, though, the important thing to clarify that you're pointing out is, what really do I mean? The question, I think everybody is clear on what I mean by x naught. I think what you're getting at with that question is, I'm gonna say it again. I think everybody's clear with what I mean by x equals 0, by the equilibrium. What may not be entirely clear, especially from that picture, is, here's where the triple equal sign comes in. I think, let me say definitively, I think it is clear to most people looking at that picture, or even looking at my picture, that we're talking about a mass that happens to be stretched to 15 centimeters away from its equilibrium position. Like, that is what I'm trying to say, and I think that's what everybody probably, hopefully thinks. But what is strange is, what do I mean really by starting the mass? And that's why the picture is funny, I guess. Like, I'm telling everybody, imagine that this mass started at 15 centimeters away from equilibrium. What's reasonable to say is, well, what do you mean by start exactly? Like, first of all, can't this thing go back and forth for a long time? Like, isn't it doing the same thing over and over? Probably a lot of people might think, so what does it mean to start a cyclical process? Like, if you're just going to keep repeating it. Or second of all, what a lot of people might correctly say is, who cares when you started your experiment? Like, what does that have to do with the actual science of what's going on? Like, Mother Nature doesn't care when we started. So what do you really mean, Yaverbaum? The picture's unclear. What do you mean by saying x naught is 15? Do you mean that the thing is literally at 15 right now while we're discussing it? Or do you mean that at the beginning, when the fictional person started this, it was at 15? Like, what does that mean? And it is a good question. And what the answer is this, what I just circled right here. What we really mean in physics by x naught, in a case like this, what we really mean by initial position is a place where we know for a fact that the velocity of the object was 0. And this, I'm saying, everybody who might have been tuning out for 5 minutes, fair enough. This you might not have thought of. Like, really, I could start the object at 15. That's the obvious thing I could do. Or I could start the object at 15, or I could start it at 15, let this thing go back and forth a bunch of times, come back to 15, 5 minutes later, and still call that spot X naught, even though it's 15 minutes later. The reason is, what I'm really trying to say is, consider that the place where this object somehow was at rest. Like the spring was at rest at 0, but somehow someone pulled it out, held something at 15, held it there. So now we have an object at rest at 15, and then let everything go. Truthfully, what they even could have done, if we like, actually, is they could have started it even closer in. They might have started it closer for 15, but started it with a push, like with some initial velocity or something, so that it popped out to a farther distance and continued its cycles from there. I'm saying at the end of the day, for me to say X naught equals 15 really means that even if we just walked into this experiment, that 15 is the spot where this object sits still, even for a moment. Like sits still, either because it's not doing anything forever, or because it just slowed all the way down and it's about to turn around and speed all the way up in the other direction. Like X naught really means a turning point. That's what and so I'm sure I don't know which of my diagrams is better or worse, or how much of a mess I've made of diagrams at this point, but that's what I'm asking everybody to picture. Picture a spring that has a natural equilibrium position, but then we set something in motion, and we set it in motion from that spot of 15. Okay, way too long of an answer, but does that answer the question at least, or sort of, or no? I think, is the diagram still backwards? Is that the point?
No, it works out now.
Oh, great. Okay, thank
I
you.
mean, Professor, we could just like you said, we're just assuming, even though if it's at 0.15, it's the origin, it's the starting position. So you can,
Yes.
as long as it's we're measuring X, so the more, so that's the only thing that really matters. So as long as you know what's the distance.
Yes, totally agreed. Yes, which is a very polite way of saying that I probably just said too much on that, but yes, totally agreed. So that said, I think this is the situation. I think it's always, if this were an exam or something, it's really good always first to have a diagram of the situation. Like what I'm saying is, we all love diagrams. We need diagrams all the time. Diagrams actually solve things for us. But before you even have solving diagrams, it's great to have a picture that just presents everything. You'll know it's a perfect picture if the goal really of a starting picture is to make sure that every variable name that ever gets used in the problem later is a label in that picture. Truthfully, that's actually how we define all those variables, is by that opening picture. So now from here on in, supposedly V naught, X naught, all those things will have meaning to us because of the picture. So we can go on and we could say, okay, question one, I'm on the next, yeah. Question one is, once you let this thing go, it'll start coming. I hope everybody understands. We pull this thing out, we let it go, it starts zooming in toward the equilibrium position. It's going to arrive at the equilibrium position with some speed, because it's going to be moving. So the question is, what is the speed at which with which it arrives at that equilibrium position? First, I'm just going to say the answer, just so I can like cut through this. The answer to the first question, which I bet a lot of people got right, I hope, and I'm just about to forget. Oh my God, the answer is the square root of 15 with 3.87, something like 3.87 meters per second, right? Is that? Did anybody get 3.87 meters? Oh, unless I'm thinking the wrong first question. Sorry, what is the
First question is the, that's not the right first question.
Oh, sorry, the first question is the force. I'm sorry.
The force, yeah.
Thank you. I'm sorry. We made the sheet longer. I forgot. Okay, sorry. So the first question is, what is that? And this comes down to this. I'm writing, so the answer, yeah. Hold on. I'm doing this the long way here. There's no way any of you did this much work to get this answer, but technically this is how much you'd want to put down if you weren't sure of what you were doing. This is, right. I mean, it's not meant to be a trick. It's meant to be, blah, 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 blah. But so basically we have,
-30.
right? Is it? So I think the answer is, if the first question is what's the force exerted by the spring, I'm saying it's -30 newtons. I'm actually, you don't even, that first line I wrote out of habit because you almost always need it, but you don't even need to hear. Is that what everybody, I mean, that's what I think for the first one. Is that, yeah, should I go? And again, if you didn't do it, you can still do it. But if you did do it, I assume people got, or please tell me if you didn't get that. I'm not trying to. But that's supposedly physics 1 material still, like it's Hooke's law, it's how a spring works. I will re-talk about it, but I don't want to bore anybody right now. Then the next question I assume is what's the acceleration at that moment, right? Is that the next question? So what is it? Yes, thank you. Oh, thank you. You're right. Okay, so now here's where you might just say, oh, divide by m. Strictly speaking, though, what you really should do, though, honestly, is this. You should do this and then say, oh, okay. If you, sorry, that's supposed to be an X. Like this is an example right here where I'm dragging this, I'm adding a couple lines that I'm sure you didn't if you did it in your head, and that's fine as long as you got it right. But if you don't know how to get it right, this is how. And this is also just like a model of what I think it means to solve these problems. Like this is the way I, now the negative kx part on top, we had already figured out, sure. And this is this.
In the diagram, did we designate which way was positive, which way was negative?
Oh, that's a great question. That's a great question. And it's really important that we do. We did accidentally, implicitly, only in that, you're right, I should have made that clear, but I'm saying since the problem said that the initial position, since it called the initial position positive 0.15. So although I should have made this explicit, you're totally right. I'm saying that whatever is on the, whatever goes in the direction.
The negative is going towards the 0.
Yes, that's what I'm saying. That's yes.
So you could just say 30 towards the 0 instead of.
Yes, that's also true. Yes, right. So, and it's true to whoever just asked. I agree with that answer, but whoever just asked, I think it was Ayeta, but I'm not sure. Whoever just asked, it's also true that we always do have to make a choice about positives and negatives, and we could have made a different choice here too. It is true. It's just I just accepted the choice as it was. I just took that 0.15 as literally positive 0.15 and went with that. But you're right. I shouldn't be that. But so then we get.
Did you say it was 30 newtons or negative 30 newtons?
So I think the force really is negative. If we make a designation that anything to the right of 0 is positive, then anything to the left of 0 is negative. In other words, if that position really is positive 0.15, then strictly speaking, we really have to say that the force really is negative 30 or whatever, because the force of the spring really is pulling the object against the direction from which it was originally extended.
But if we started off from 0, it would have been considered as a positive 30 newtons, or no? If we started off 0.
Well,
instead of starting off from 0.15.
Well, put another way, I would say if we started off with, or if at any moment, and we'll see this in the problem, but if at any moment the object finds itself on the other side, like if this thing is going back and forth, if it's a spring that's can extend and compress, which we are assuming actually. So at any moment that object gets to the other side of 0, which it will, then whenever it's on the other side of 0, like when it's at position negative 0.15, which it will be, then at that moment, the force will be positive 30 because the force will be pulling it. The force is always pulling it toward the 0. So if we're on the negative side of 0, we get pulled positively. If we're on the positive side of 0, we get pulled negatively. Does that make sense? Like on the diagram you're looking at, is the 0.15 to the right or to the left of 0?
It all depends on how you drew it. I drew it in my.
Wait, but I mean the diagram in the actual problem that isn't there diagram? What's that?
I don't think it specifies.
Wait, there isn't a picture in the original homework problem?
So there is a picture, but it doesn't really say which way is which. That's why I was asking the initial question.
Oh, well, that would be a very good reason for you to be asking that initial question. Oh, that's.
I think in the picture though, it did have it showed that the force of the spring is pulling it to the left.
I mean, clearly I should just get out the picture myself.
Yeah,
but the one thing I just want.
If you look at the picture.
Okay. Could someone actually just upload that? If you look at the picture, the picture should at least, if nothing else, does the picture make clear where the 0.15 is? As in, is the 0.15 spot that we're talking about, is it to the right or to the left? The picture doesn't make that clear?
It says it's to the right.
Okay, so that's
to the right.
Okay, so here's the thing.
And then it marks the X and Y axis too, like the direction of them.
Oh, okay. So, well, that's helpful too. So, and all these discussions will get shorter as we go. I know they drive some people crazy. Like the more meat we have, the more meat, but this is super important and reasonable. Like, because it's true, you always have to have your coordinate system all straight in your mind before you solve a problem. And it's also true that you can choose whatever coordinate system you want, and you should, and make it to your advantage. That's the power of physics. But it's also true that if someone's already sort of made it for you in the problem, it's good to try to stay consistent. So I am saying right now, according to this picture, 0.15, sorry, I'm just admitting someone. If 0.15 look, and you're totally right to have asked about those dotted lines. The dotted lines are meant to make it clearer. So if they're not, then that's bad. But sorry, if the 0.15 is to the right of the 0 in that picture, then that necessarily means that right is positive, and that negative 0.15 would be to the left of the 0. And the mass will end up in those negatives. Like, there's questions about this, but let's get it straight now. The mass will find itself in those negatives as frequently as it finds itself in those positives, not because the spring is like flipping over or like doing a time warp or something. Like one part of the spring, one side of the spring, I believe the left, is meant to be rigidly attached to a wall. It's the other edge of the spring that we watch move back and forth. And to make this super clear to everybody, because it wasn't clear to me originally, that edge does move back and forth. Like, it can go in as easily as it can go out. A spring can be squeezed as easily as it can be stretched. And it's not, we're not saying that we're going to squeeze the spring down infinitely and self-destruct. We're just saying that it's squeezable enough that the far edge can get as far to the left of its happy place as it can get to the right. Like, it can squeeze as much as it can stretch without breaking. So to bring this back full circle, I am going to say, when that mass ends up at position negative 0.15, at that moment, I'm going to say the force acting on it is positive 30. Like, the force necessarily has to be opposite to the displacement. That is the meaning of Hooke's law. That's the meaning of a restoring force. Like, in other words, I really am believing this part of the law, the negative sign. And I'll say right now too, sometimes when I know I can get away with it, I might not care. Like, I'm not saying that the negative always matters. Sometimes it does, sometimes it doesn't, but it is always true. So I think, to bring it back to this, I'm saying for answers, the answer to question number 2, I think the acceleration is negative 100, or negative 100, yeah. The acceleration is negative 100 meters per second squared, which just means that it's accelerating in that direction towards 0, which strictly speaking in physics means it's either moving in that direction and speeding up, or possibly moving against that direction and slowing down. But this is the answer to question 2, I believe. Everybody good? Are we good? Good, not good? Wait, I'll look at the chats. Oh, and I know, by the way, there have been a couple of private questions which are so great, I almost accidentally answered them in public, but I respect the fact they're private. So please remind me at the end if I have missed a couple of private questions. Oh yeah, well, and one, if you submit anything cool at all to me ever in the semester that has to do with physics, ideally with physics that's somewhat related to this class, but if you put in effort into something that can help someone else either understand physics a little bit more or like physics a little bit more, yeah, I will definitely consider giving extra credit to that, even if it's not exactly the material we do here. I think it's probably a safer idea to work on things that we do here, because it'll just all help us more. But yeah, that was just a question I got asked at some point. Okay. Are we good with, should I go on to the next question? Okay, I believe the next question is, now we start getting into speed stuff, right? The next question is, if it starts racing toward the equilibrium, at what speed will it pass through the equilibrium? Am I correct? Is that the next question?
The next one is the acceleration at equilibrium.
Oh,
No.
Thank you. Fair. Thank you. I stand corrected. All right. So the next question is, yes. Sorry?
No, nothing.
Oh, okay. So great. Yes, that's not what I thought. So the next question is, assume, so this thing is going to start moving in. It's going to start moving in. I think everybody can picture that. I hope it's going to, its destination is the equilibrium. So it's going to get to the equilibrium at some point. And at that point, it's going to have properties that we can use to describe it. And one of them is acceleration. So the question for this one is at x equals 0, what is a? And I'm going to cut straight to the chase and say, well, I think a equals 0, which I'm sure many of you do think also. I mean, and so I do think the answer is 0. One reason I think that is because we are saying this. And so if, I don't want to but
what you mean by x equals to 0 is basically when x is at 0.15, which is the starting position,
oh no,
right?
Wait. Great question. But no, and that's why the triple equal signs and everything are important. No, when I say x equals 0, what I mean is when the thing is at equilibrium. X equals 0 to me means the equilibrium spot, not the first spot. Like the first spot is x sub 0 equals 0.15 or whatever. Do you see what I'm saying? Like that. That is the confusion I was sort of trying. Maybe I was speaking about too earlier, but like x equals 0 doesn't mean the very first place that the thing was. If the thing started at 0, it would never go anywhere. Like if you just have a spring that you attach to the wall and you just like let it sit there, and then you put a mass on it right where it's sitting, then the mass will just keep sitting there like you did in lab, I think, kind of. But if you start a mass somewhere else other than 0, and let it go, then it'll start moving. So we're very specifically saying that the place, like we're really saying at time equals 0. This is what I mean by triple equal sign versus sorry. I'm saying that x sub 0 means the place where you are at time equals 0. Like that's what the notation means. But where the value of it might or might not be 0. And in here definitely is not, because if you started at 0, you wouldn't go anywhere. So when I say x equals 0 here, what I mean is the equilibrium spot of the spring. The spring, am I making sense? Is that, oh, look at the chats. Okay. Oh, the chat. Well, yes, that's true. Wait, I'm looking at box. Yeah, I think. Okay, I think we're all on the same page. Are we on the same page? People, I love how people are helping each other in these chats things. Oh, you guys cannot send private chats to each other. Is that right?
No, we can.
You can't? You've tried on this?
Yeah, if you just change who you're sending it to, I think.
But have you tried actually sending it to someone who isn't me, though? One of you should try sending something to one of you that's not me and see if it works.
I think we're not able to.
Yeah, I think you're right. And I think I will change that if I can't fix this breakout room thing. I mean, there's reasons for it. I will change it, but as it stands, I either have to change that or fix the breakout room thing. By the way, to everybody, and I do want to move on, but I have looked into the Discord thing. I took that very seriously. I will still, I'm going to look into it more because it does seem, I see the point, but I also looked into whether, I don't think I can do it as a professor. I think I'll get in trouble, basically. But I will keep looking at it, and I do think it's a very helpful suggestion. But all right, for now, I'm saying we're asking what is the acceleration of the mass at the equilibrium position, and I believe the answer is 0. I think I just showed that in the computation. That doesn't explain anything physically yet, but I will start explaining. But yeah, I think if the mass is at equilibrium, that means that the spring is not exerting any restoring force on it. And that makes sense. It can't. I mean, if x equals 0, F has to be 0, if for no other reason that if x were 0 and F weren't 0, what direction would it pull? Like it literally, the spring wouldn't know what direction, whether it's trying to extend or compress, because the thing's already there in the center. So if x equals 0, F is 0. And if F is 0, then A is 0, because there's only one force acting on the spring. That's important. The reason I keep writing F net equals MA down before I even write F equals Kx or negative Kx. F equals negative Kx is the force exerted by this spring. But no one in physics ever said F equals ma, right? F net equals ma. The sum of the forces equal ma. So whenever you're trying to go from forces to accelerations, you need to account for all the forces, ideally in a free body diagram. Just here we're lucky. There's only one force horizontally. So, okay, all of the forces together, is still just that one. So I say A equals 0. I say I'm going to move on because I think we'll use that 0 more and make it more clear in the next. But the next question then is the next. Oh, yes, I'm sorry. Yes.
Number 3, your justification was that Fs equals 0, or would we just be able to use the same process we did in question 2 by plugging it into Newton's second expanded, and then that way we'll be able to directly say acceleration equals 0?
Oh, right. I'm sorry. Totally. The second thing you just said, yes, because we already got the force and I had forgotten that. Since we already got it, you could just go directly and use that. Yes, I just sort of forgot that we'd already gotten it. Yes, you're absolutely right. Yeah. I think I'm just saying this, if this were an exam or something, I think I'm just warning everybody that somewhere in there you got to write down the F net equals ma part, and you have to show them. But yes, I totally agree with that. All right, so the next, is it good? So the next question, I believe now, is what's the velocity, the instantaneous velocity of the mass at that moment that it's at equilibrium? Is that correct that that's the next question? Yes. Okay. Thank you, Gabriella. I saw that nod. Thank you. Yes. Okay. So this is the one where I believe the answer is approximately 3.87, which is like the square root of 15 or something. It is approximate. That's not inaccurate, but it is like you have to chop off. It's a square root of a. It is an irrational number, but I believe it's 3.87. So if you got that, I think you're right, and that's cool. But I'm going to go. Did anybody get? Well, I won't ask that yet. But now how I'm going to get that is a slight shift. It's still old physics. Like, okay, we're practicing the old physics of F net equals ma. That's never going to leave us in physics. We're using the old physics of F equals negative kx. Okay, also never going to leave us. But now to get speed at that point, it sounds like a similarly simple question. But speed is trickier now because if I just continue in the same mindset that I might have had a second ago, if I'm thinking of kinematics, accelerations, velocities, and forces like I just did, I might think something like, so this is question 4. Question 4 is at x equals 0, what is v, right? This is our question, stop me if I'm wrong. And notice, by the way, I'm saying what is v? I'm not putting a bar over the v. So we're not asking about average velocity, we're asking about instantaneous velocity. So some people might, okay, I'm about to write down some things that are wrong, just to be, like, you might think something like, oh, you might think something like that. Students often do. And I would say, be very careful. First of all, like, that's not even right. If you're going to ever say anything like that, say this, like, is it true that velocity equals displacement over time? Sure it is, if by what you mean by that is average velocity, right? Like the most, like that is true. Average velocity equals displacement over time. That's totally true. Average velocity does. Velocity at some instant does not, but average velocity does. But this problem isn't asking for average velocity, so that's not going to help me. I might go one step smarter and I might think something like, oh, I remember though, I just got an acceleration and I know my old physics, so I'll do something like this. Sorry, I'll do something like this. Which is true, like average acceleration by definition equals change in velocity over time. You might think something like that, and you might even be clever enough to say, okay, I'll rearrange it and solve for v like this. Now I'm writing all this in red because it's not right. Okay, don't write it down. But I mean, it's true facts, but they don't help us in this problem. You might say, oh, v equals at plus v naught. Then you might even say, oh, but I don't have time. Crap, like, I guess that's not right. And let's pause for a second. Let's say this is an exam, right? I'm asking a question you haven't answered yet before, and you're a good person. So you maybe write this down because it is true. Like you start, say you wrote this down. First of all, okay, it's going to turn out to be wrong. But the reason I'm doing it right now is you would get points. If you wrote this down right now, these statements are true. They are true and they are relevant. they get points right there. They're a good process. But now you might notice looking at this one, oh, I don't have time. So that's a disaster. Like, what am I supposed to do? Many people at that moment would say to themselves under the pressure of an exam, well, this must not have been the right way to do it. So, oh, that's bad. So, and then they'll start erasing all of this. Don't do that. The next most logical thing to do is say, wait a second, I need the time and I don't have it. So that's bad, but that doesn't mean I'm doing the wrong thing. It might mean I have to now take another step to start solving for the time. And what then happens in your brain, if you're really under pressure and it's really, if you're under time pressure, I think without even realizing it, a lot of us will say, oh, I got to start solving for the time now. But then we think, oh, that's going to take some freaking time in this exam. Like, that's going to be a process. I'm not even sure, like, and I'm not even sure if it's right. So that's going to be a big risk. I'm going to go start solving for time now, and I'm not even sure if it's going to come back and help me. So then people will really quickly, unconsciously just shut down that whole idea and be like, screw it, like this is wrong, because they have to do some extra thing. And I say again, no. If you think now you have to have time, I mean, literally the variable t, then it is always worth, if you have a plan in mind, I'm saying this to everybody, especially in the virus. If you wrote this stuff down, V equals AT plus V naught, and then you think what I need now is time, I have to go solve for it, and it might not work out, but it's all I can think to do, then do it, right? Like every bit you do on an exam is getting you either closer to an actual right answer or at least is correct work that is getting you points. The worst thing is to decide not to do, that you did something wrong just because it's going to entail more work. Now, it does happen. This is wrong. I could start solving for time now, but I have no idea how to solve for time now. Like literally, I mean, I have an idea, but I would have no idea how to solve for time now based on these facts. So I might shift my attention and say, wait a minute, all right, I tried a little bit. I'm getting nowhere. I hope I get points for that. Let me shift gears. What about some other old equation that doesn't involve time? Like, is there any equation where I'm not solving for time, but I don't need the time either? You might remember something like this. This is pretty obscure, actually, but it is part of physics 1. This is an equation. It was in physics 1. I hope maybe you recognize it, but I would almost hope you didn't memorize it because it's not worth memorizing. All right, someone's saving me time. All right, to cut to the chase. This one, you might try and it would get you closer to the truth, but you'd finally realize that Grace Carolino, oh, this is awesome, right? You're all saving me time. I like the way, this is the most polite way you could do this too. It's so cool. All right, right. Everybody's chatting right now, and they've probably been chatting for hours and I didn't even realize it. Oh no, for 1 minute. Everybody who's chatting right now is even more right than they know. Sorry, is it Aliyah or Aaliyah? Aliyah or
Aaliyah.
Aaliyah, okay. What Aaliyah said is exactly what I'm going to do. And I'm on purpose showing you the wrong stuff so that we can all relate, whatever. But I am going to use kinetic and potential energy. I am. And I'm going to say, not only am I going to use it because it can work, as she's saying, but actually I have no choice. This is exactly a circumstance where actually you have to move from the acceleration force way of thinking to the energy way of thinking. That's the hard part of physics, is knowing which kind of thinking to do when. The giveaway is the reason we're going to do energy and we're not going to stay on this anymore. Well, does anybody know what? Like, and then there's Diffie Q. We're getting to that too. Thank you, Antonio. That's badass. We're going to get to that, believe in a couple of minutes, actually, and then I'll call myself a badass. But why right now we're going to do energy rather than forces is for a very concrete reason. Like, we actually can't use the forces and accelerations as they stand. We have to use energy, the second chapter of physics. Can anybody tell me why? Like, why? Oh, please no. Oh, please no. That's funny.
Is it changing accelerations like?
Yes, exactly. I didn't mean to cut you off, but yes, you sounded, yes, like, because the acceleration is not constant, boom, we can't do anything with A equations. They all assume there's an A. That doesn't change, but it's changing. That's exactly, whenever acceleration changes from position to position, you must think energy conservation. Whenever acceleration changes from time to time, you can also then think momentum conservation. But as long as it changes position to position, you think kinetic. So we're totally going to do the energy thing. I'm going to get to it now, whatever he's saying. Oh my God, I know, I'm boring myself. This is, which question? This is question 4. Okay, we're back in yellow. It's like this. The correct thing to do is this. The correct thing to do is exactly what she said. And if you do it correctly, you should get the answer 3.87. So if anybody wants to try that. But yeah, it's this. Sorry. This is the way I write it. I'll explain it more and more, but I'm saying energy conservation means that the sum of all of the energy, the total mechanical energy, is the same at every place. This is a subtlety that I did not realize for years and years and years learning it or teaching it. Depending where you took physics, you might not have made this connection in your mind, but let me say it again. What of course, energy conservation means total, of course, energy conservation means that the total amount of energy is conserved, never changes, stays the same, like yes, and that's, but specifically with energy, what that means is it doesn't change from location to location, as opposed to saying from time to time. Energy conservation means the total mechanical energy at any one given spot is the same as at any given other spot. So the way I always write it is this. I always say like, oh, all the kinetic plus all the potential at any one position, call it position A, will be the same as any other position B. And then I fill in what my A's and B's are for the particular problem. So here, in other words, here I'm saying, okay, the total amount of kinetic plus potential at, let's say, x equals 0, the equilibrium position, must equal the total amount of energy at any other spot, in this case, spot 0.15. In other words, always of the two spots that if you're using energy conservation, it's because you know the speed of something somewhere and you don't know it somewhere else. So the two spots that you always compare are the spot that you know something about and the spot that you're solving for. That's what we have here. And also, by the way, I am saying triple equal sign. I'm saying from now on, total mechanical energy, capital E, by definition means all the kinetic plus all the potential of some system or some object. That's the thing that is conserved when energy is conserved. So I'm just going to keep filling in now. So yeah, I'm saying, okay, kinetic energy is always, in this class, pre-1905, kinetic energy is always 1/2 mv squared. That one you can memorize or whatever. If you, all these things are given on the equation sheet of a test anyway, but sorry. So, and potential energy, it's more complicated, but for a spring, it's this. We have to get back to that, but it is, for a spring, potential energy is what I just wrote. So I am saying that this sum must be this, the sum must not change whether we're at the equilibrium or at anywhere else. And now I start filling in bit by bit. Notice another habit: whenever solving problems, when you're doing homework, when you're doing exams, when I'm doing, I strongly urge everybody to leave number plugging in for the very last step. Always postpone numerical quantities as long as you can doing a physics problem, especially in this class. The numbers really disappear from this class about midway through. Everything is letters, everything is variables. It looks like math more than physics because we're trying to figure out everything in general. Like, we don't care about some particular spring that happens to have a mass of 0.3. We're never going to see it again. So whenever you're solving a physics problem, it's best just keep everything general until the last possible minute, plug in numbers. And that means that now, before I even plug in numbers, first thing I'm gonna do is plug in any zeros that I can to simplify this. Like at x equals 0, we already established there's no acceleration, there's no force, and indeed, similarly, there's no potential energy when x equals 0. I mean, I think sort of computationally evident. And similarly, when x equals 0.15, when x equals 0.15, one of the reasons I spent all that time at the beginning of this problem establishing these is I believe it's, by definition, we can say that when x equals 0.15, when it's out there at that initial position where we held it to start this whole process, we held it there, we started from there, its speed at that moment was 0 out there at 0.15. In other words, this is true. So now what I'm saying is, sorry, this is starting to get illegible, but illegible. But I'm saying that now, and again, I know in my heart, if you got this problem right, which I think a lot of people did, probably very likely your very first line that you wrote down might have just looked like this thing that I just wrote. Like maybe you didn't write the first 3 lines that I'm talking about. And I'll always say that's fine if you know what you're doing. You can skip steps in your mind, but the whole purpose of the steps is to help us all when we don't know what we're doing, as in the next question. So I'm saying, well, I just wrote this, I'm just rewriting it. I'm saying that what I'm really trying to emphasize right now is don't say 1f(mv) squared equals 1f(kx) squared just straight up. If you just write 1f(mv) squared, that, because it's not true. That makes it look like at some particular spot, this thing has an equal amount of kinetic and potential energy. If you just say 1f, well, you'll see. And that's not what we're saying. I'm saying that the amount of kinetic that this thing has at equilibrium is equal to the amount of potential that it has at x equals 0.15. Those are the 2 numbers that are equal because there happen to be all these zeros making our life easy. So I'm ultimately saying, right, I'm leaving the numbers for last. I'm saying that I believe all this work that I'm doing right here actually looks like good physics to me that actually makes sense. No matter what particular details there happen to be of this spring, it seems to me that this is right as long as I'm looking for the equilibrium position speed. And so then when I do finally put in the numbers, you know, I get something like,
When you're done writing this out, would you be able to go to the last page?
oh yeah, definitely. Thank you for reminding. Yes, and yes. Hold on a second. And also 0.15 squared is 2. Oh yeah. Someone might want to check me on this. I think, well, I know the number I just wrote down, I might have done wrong in my head. Someone might want to check me on that, but I think that this does all end up being. I will go back to the last page in a second. Well, here, yeah, I'll just do it. This page you're talking about? Or the one before it?
This one, I just didn't get down the last part. Okay, I got it.
Yeah, no, good. And thank you for asking. I'll do that. Happy to do that. And that reminds me also, I believe you guys got the warning when you signed in today. It told you it was being recorded, right? I hope. Yes?
Yes.
Great. So all this is being recorded. So all you can, I may not do it right away. Just please, from here on, and you can all assume that anything we're doing now, I will post as soon as I can, like that night or something. And I'll try to edit out. I usually just try to chop off the first 10 minutes when it has nothing to do with physics. But anyway, yeah, you'll have access to this tonight to re-scroll through and stuff like that. Okay. Yeah, so I think any questions on this so far? Could you just remind me one other thing? Hold on a second. Also,
I was looking through the textbook to try and figure out how to do this, and it was showing me like a whole chapter on like harmonic equations.
I'm listening. I'm totally listening. What about, yes?
Go about using that method instead, because you wind up getting like the same answers.
Right, and we're getting to that. But wait, are you asking, are you allowed to do that, or?
Yeah.
Yes, you're allowed to do anything that's correct, and we're about to. But it's also, my real answer is at any moment anybody's allowed to do anything that's correct. But I would strongly always encourage everybody to at least everybody should still hear and know my way of doing things because there's usually a reason and it gives you more options and blah, blah, blah. But right, no, you could do it anyway. What I'm trying to do here though, is show how all that stuff, which is hard and out of nowhere to a lot of people, I'm trying to show how all that stuff comes from this. But yes, anything that works. And you also just reminded me with a small,
In our notes, like for homework and exams, when we plug numbers into these equations, do you want us to include the units or no?
yes, please. That's also a good question. I do want units, especially in the final answer. I really want units, and I think it's good for everybody while they show the work. I think the units help you do the work. But yes, in the final answer, I really do. Yes. And again, I'll get more. And all these kind of. Oh, I'm sorry. Go again. What?
Like in the work when we're doing it, like for the first line that you have here, should we have plugged it in as like 200 newtons per meter and etc.?
Right. So that's again a really good question. And my answer to that one, and hopefully you'll just see more and more as I do it. But like, what it comes down to is my ideal is that you would have units in those steps because they actually help. But here's the thing: in those steps, if you don't have units and you get it right, I'm probably not going to say anything, like, because I know how fast some people could think, and I don't want you, right? If you can get things right in a way that I can see was thinking, then you can abbreviate and stuff and leave those units out. It's just a good habit to keep them in, because then when you're struggling with stuff, you'll see how they really can help get it right. But yeah, I wouldn't take off if they're not in your work, even on an exam. If you don't have the units in your work, but you do have it in the right final answer, and it seems like yeah, then it's fine. But once you start making mistakes, then I'm going to look through the work and get more, I'll have more places to be punitive if it wasn't there. So yeah, but yeah, even on an exam, you do have to have it in the final answer. You don't have to have it in the work. Quick side thing that someone just reminded me, just for ideas, both ideas of extra credit, of how to get extra credit, but also as the course progresses, more and more things we talk about, I will try to remember to direct you to demonstrations of those things that will clarify. And a lot of those things you'll find on a YouTube channel, like the stuff that past students made or that I made, are on a YouTube channel called Infinity Court. And there's also a website. And so you can just occasionally look there for things either to help you or for ideas. And I forgot to mention, I'll also say in more detail later, I'll give extra credit for appropriate enough feedback from if anybody looks at something that someone else did, even if, like, whether from past years or this year, in other words, I will give extra credit for clicks, so to speak. We have to be careful about this, so it doesn't just like devolve into self-promotion. But if you are struggling with something and you find a video in one of our physics fora that helps you, and you can just write down a couple of sentences on a piece of paper, like, I hit this link on the YouTube channel, or I subscribe, God willing, whatever, but like, I did this link and it actually straightened me out on this, like, because of this part. I'll totally give extra credit for that too. Like, the more you guys can use each other's resources and bottom line, this virus has trapped us all in space. So let's just be more expansive in time. Let's make our class bigger and have it include past and future classes in the conversation, because we're limited in other ways. So if you find other stuff of mine or my former students and you use it and you can show that, that's extra credit too. Anyway, going on. Where do we, so that was, all right, that question was 3.87. I'm intentionally not asking people who got it right and who got it wrong right now, because I don't want that to be the issue. But I'm expecting, if we go on to the next question now, I believe that a lot of people probably got, what I believe is the question we just did is, it's quite possible that a lot of people got it right, and that's great, and they'll get total credit. It's very possible that a lot of people got it right with a lot less work than I just showed. Great, fine. But it's also possible that this next question looked identical to a lot of people, and that a lot of people who rocked the 3.87 may feel like they did the same thing and got also a correct answer here, but in fact might have gotten it wrong. So this one might be worth listening to, and let me tell you all, I think the answer to this next one coming up, if it's the question, I think, is the next question, at what position will the mass attain a speed an instantaneous speed of 1 meter per second? Is that?
No, it's of 3 meters. Per
I mean, I'm
second.
sorry, of 3. I'm sorry.
3 meters. Yeah.
Of 3. I'm sorry. But that is the question, though. That is the next question. Is that right?
Yeah.
Okay. So 3. Thank you. 3. All right. This next question, it totally looks like you're just going to do the same process and just like solve for a different variable. And that's true if you do the process right. But I think the answer to this one is 0.095, I believe, meters, 0.095 meters. Not something like, I believe a lot of people often get an answer like 1.1 or something. And that's not a difference in rounding. I'm saying this in advance, so I'll never know who you are, so don't worry about it. But maybe just as a reason to pay attention, we're going to find that the answer to this, I believe, is 0.095. And whereas you could end up getting like 0.097 or something because of a rounding issue on your calculator, if you got 1.1 or something like, or 1.12 or something, that's not rounding. That is a physics error that I want you to just look out for in this explanation that's coming. So, but I think, but if you got 0.095, like go get a beer, I guess. I don't know. That'd be gross. It's like 12 in the morning. No, it's not. 3 in the afternoon. Get a beer. All right. The next question, I'm going to solve the exact same way. But to me, that, actually, I'll go to the next page. To me, that means I'm not going to write down 1/2 mv squared equals 1/2 kx squared. Like, that was a step I got to in the last question. That looks good, but that's not how I started it, and it wouldn't be right. I'm going to start again the same way. I'm going to say, all right, the total energy at any one spot, at any one spot has to equal the total mechanical energy at any other spot. By those two spots, I mean a spot that I know something about, i.e. I know the speed, and a spot, or I know something about, and a spot that I'm solving for. Now here, so a spot that we know something about, well, certainly the equilibrium, because we began with that, but now we've also just solved, let me start again. We know something now about both the equilibrium, because we just solved for it, and we know things about 0.15 meters. So one of these two positions that you use could be either of those. I'm gonna use the equilibrium just to stay consistent. I'm gonna say, oops, sorry. I'm going to say the total amount of energy at the spot that I'm looking for, which is an unknown spot, right? I'm solving for a position. I don't know what the position is, but I know that it's the position at which the instantaneous speed of this object is supposed to be 3 meters per second. So that spot, the total amount of energy there that I'm looking for must still be the same as the total amount of energy everywhere else, including the equilibrium. So now I'm going to fill in, and I'm going to say, all right, at the equilibrium, we already. I'm writing the same thing again just so I can do something to it. All right, I'm going to say at equilibrium, it's still true that the potential energy was 0. Like we said before, that's still true. The kinetic energy is something that we now know because we just figured it out. Okay, I'll put that in a second. But at the, my bad. Sorry. The other spot is wherever v equals 3 meters per second. You know, we don't know where, that's what we're solving for. But at that spot, v equals 3 meters per second. So there certainly will be kinetic energy at that spot. I guess my big point here is I can't cross out either of the two terms on the right side of this equation the way I could in the last step. In the last step, each side, there was a term I could cross out. So I ended up with a very simple thing. Here, I won't end up with something as simple. I'm saying, in other words, this. I'm saying, okay, I can divide both sides by 1. Like I can factor out a 1/2 from both sides and then divide both sides by 1/2. So the 1/2s are gone. That's nice. And now it looks like I have an MV squared on both sides. So you might even think I could subtract it from both sides, but no, it's two different MV squared, like it's two different V's, right? That's the point of my notation of where I put these little subscripts outside the parentheses. In other words, I'm saying, and I can turn back the page in a second, but I'm saying, well, and so yeah, and it can't cross out by the can't divide both sides by m because I can't factor it out. So the m is still there. So I know over here we have and that's that number. That's I believe, and this is. Oh, sorry. Oh, bad. Wait, you can. Nothing I'm saying is wrong, but it's not in the order I want. Sorry. I still want you. I'm still want people to be in the habit. I'm saying this. Remember, we're solving for x. We're solving for x. So I really do think it's a good idea to say. Okay, now this is starting a little clunky. Again, it's strong advice on my part to plug in the numbers at the end. It's not, you may not always like doing that. Oh, someone's in the way. And so then we have.
Professor, where'd you get the 15 from?
Good question. Very good question. The 15 is 3.87 squared, I think, but maybe I'm reading it wrong. It's supposed to be V. That's the 15 is supposed to be because I'm using the V of 3.87 that we just solved for before. Let me check if I'm right before I say. Yeah, like okay, I skipped this. Sorry, that's a good question. I'm just going back. So if the step that I'm doing is mv squared at equilibrium position, and v at equilibrium position is 3.87. So 3.87 squared is 15. Does that am I making sense? Like I'm saying I'm saying this is the part I was doing. 15 is v squared if you use the v that we just solved for in the prior question. Does that make sense? So is that, I forgot who was just asking, but is that okay? Yeah. 200, 100. Yeah. So I'll let this sink in for a second, but are there I mean, is it, or raise your hand if you raise your hand electronically when you want me to move on. Like if you don't raise your hand, I'll assume you want So once you're ready for me to move on, please electronically raise your hand. And I won't move on until then. Thank you.
When you did this, were you using the velocity and the position at equilibrium?
Right. Yes, I was using the velocity at equilibrium for, yes, I was. But that, so I used that to get that 15. Let me move back a step in the thing. The key is every time I'm saying at the bottom, like where I'm talking about. So the MV squared, this MV squared is at equilibrium, but this MV squared is at the spot that we're looking for. So in other words, I'm actually never using the 0.15 in this part of the problem. I would either use the equilibrium or the 0.15 spot, because those are both spots that we know all the facts about at this point. But
that was the spot that I used. I got the same answer, but I just want to make sure that both ways are fine.
oh yeah, I'm sorry. Oh, and you're Gabrielle. Sorry. Yes, totally. Yes. Got it. Yes. Right. Sweet. Okay. And then I'm thinking, should I move? Oh, and that seems good. Thank you. Okay. Oh, cool. All right. So 10 p.m., 11 p.m. And so again, if you're ready from, oh, I'm sorry.
Hello?
Go on. Yeah.
What was the final answer?
Oh, so sorry. Yeah, the final answer is 0.09. Yeah, the final answer in blue is 0.095 meters approximately.
Yeah, I got the same answer. Okay, thank you.
Thank you. All right, good. So it seems like we're doing good here.
Thank you.
What's
Okay,
that?
thank you.
Plus or minus 0.095?
Oh, yeah, you know, that's a great point. I don't even know if that, you're absolutely right. Absolutely. And clearly, if you didn't put plus or minus on any word exam, I wouldn't take off because I just totally forgot that. But you're absolutely right. That's a good point. Yes. Yeah, it could be either in English, this thing will achieve a speed of 3 when it's on either side of 0. Very good point. Yeah. I think I'm going to move on unless it seems like I got a lot of hands that say they're okay. But I hope and again, look, I have a ego or self-esteem like anybody else. So of course, my worst nightmare in a way is that I'm boring people crapless at every moment, of course. But really, that's really my second to worst nightmare. Of course, my worst nightmare is that I'm totally confusing everybody all the time, right? So why I'm saying that is at the beginning of this class, right now, if you experience a lot of boredom, good, fine. I mean, I apologize. Like, I don't want it to be boring. But if you feel like things are boring because they're clear, if you feel like things are boring, that at least I hope means that things are clear and not fast enough for you. And I can tell everybody, this will speed up. If you're getting worried that this is going too slow, I don't think it'll stay that way. But I think we can go much, much faster in general, on average and toward the end. We can go much, much faster if we go super slow at the beginning. Like, it's all about fundamentals. So please, everybody, forgive me if for anybody this is going too slow, don't, just hang in and have faith. The material will get thicker. But for those of you that this is going too fast, or it sounds like please do keep asking, please do stop me. Like, we need to know where everybody is before we move on. So like, I'm about to move on, but I can't imagine a question right now that I would consider really bad other than like, why does my mother smell? Like, that would be a bad question. But she doesn't, by the way. Thanks for asking. But I don't mean she doesn't have a nose either. But anyway, any questions on this? I'm good. She's good. I'm good. All right. I'm gonna move on. All right. I'm gonna move on. All right, the key point of that whole thing, though, by the way, was you would not get that answer right if you just said 1f_mv squared equals 1f_kx squared. And a lot of people think that that is a statement of energy conservation. It's just not true. Like, kinetic does not equal potential. The sum of kinetic and potential equals a constant. Like, that's what's true. And here we have a case that just is trying to show, unless you have the coincidence of kinetic and potential terms dropping out as 0 everywhere, which is very special cases, things are not that simple. So we always start with always start with something true and then make it relevant. Don't start with something relevant and then try to make it true. Like that's what politicians do. We're physicists. All right, moving on. And I mean politicians from both sides. I don't care what's that. All right, moving on. The next question is, oh, now it's a couple of English questions, I think, right? Is the next question, could someone just tell me the next question?
It's how much will the string compress where the mass stops moving?
Great, thank you. Right, okay, great. Right, and so we've sort of have accidentally set, so that question, the answer is, right, what they're basically getting at there is what I was trying to say before, that whatever is the initial extension of this spring, if by initial we mean that the mass was originally at 0.15 and had no speed there, like if it was let go from there where it had no speed, what we're now saying is, oh, well, that will be the maximum position on the other side too, necessarily. Like if it started at positive 0.15, then it'll get as far as negative 0.15 on the other side and then turn around because energy is conserved. 0.15 represents a position where all the energy was potential, none of it was kinetic. So the only spot on the other side where there could be no kinetic, i.e. a stationary turnaround point, the only place where all the kinetic could be the same, 0 again, would be a place where all the potential was the same again. So it's 15 on the other side. That is the answer to that one. And then question 6, I think I asked something in English like, how many times can the mass keep doing this or something? And the answer is infinity. Sounds like a dumb, oh, sorry. Is that not the next question? I'm sorry.
Yeah, that is. But for the previous question, that's actually labeled as 6 in the document. But also for that, what did you, like in the homework, you have a whole rubric set out. So would we be fine if we just wrote x equals negative 0.15 meters, or would we need to add a justification in order to
Oh, yeah. All right. That's fair too. That's a couple of things like that. In general, whenever in doubt, always put a justification. Like I'm trying to be a little bit faster now because I'm like afraid of boring people and stuff like that. But when in doubt, when in doubt, always put a justification. It is true that there's a little bit of a flexibility and intuition here where the thing about the justifications is you can sometimes get away with not having them as long as you're right. But so the more confident you are that something is straightforward, sure, you can write it straightforwardly, but really there's no harm, like even one sentence or one statement would really be helpful. Let me get back to, that's a very fair question. Let me get back to that because I think right now what's happening is I'm starting to get nervous that I'm talking so much about this class and not enough about physics that I'm trying to compensate by going a little faster in the physics. But I don't want to send mixed signals about how you're supposed to do it. So yeah, I'll try to be more careful about putting in the justifications and things here that you really should. But sometimes here, my justifications are coming out vocally. I'm speaking, so then I forget to write them down. You're right. I should be writing them down. But do you agree with? I think that was Ayeta. Do you agree with both those answers, though?
Yeah, I do.
Okay. So for the moment, I'll just say you dock me points. As long as we both agree, then we're both good for the moment. But yeah, you should always have a justification. But if we agree with those now, and by the quick thing too, question 6. I'm saying infinity, which of course sounds very unrealistic, or also sounds like, well, yeah, I mean, if that's all you were looking for, like, why do you even bother asking? Like, okay, you're talking about a perfect spring. Please understand too, this whole issue of perfection or ideal or imperfection and approximate in physics. This is also where triple equal signs and double equal signs can help. What I'm saying here is I'm not dumb. Like I know realistic springs are not they don't tend to go on to infinity in physical reality. But that doesn't mean that what I wrote here was a lie or useless either, because the spring, we were told here that the spring is an ideal spring, a Hooke's law spring, i.e. that this spring is not experiencing friction. If it's true that it's not experiencing friction, then this infinity answer is right. And then people will say, well, okay, fine, but that's textbook. In reality, everything experiences friction. True, but the real key point, how we do physics is this answers that we're getting here are the answers for what would happen if we sorry. What we're saying is here, there's two issues. There's issues of springs and there's issues of friction. The only way we can understand how to deal with the world, which includes springs and friction, is if we understand springs and we understand friction, and then we understand that the two are being put together when we have realistic springs. Better and better springs have less and less friction, and that's how we know what would happen with a spring with no friction. So what we're really always doing in this class or in physics is we're always dealing with one variable at a time in the hopes that then eventually we put them all together. So this spring intentionally has no friction just because there's enough spring issues we're looking at here to keep us busy. We can at any point put the friction in and then deal with that too. But as long as it says no friction, then the answer here is infinity. Not that anybody's arguing it, I know, but they just might be wondering why it's useful. The answer here is infinity, and it's useful because then if we go on to the next question, which I believe is the one that starts asking about what happens to the speed, the acceleration, and the jerk, and so forth. Is the next question the one where it says, assume that the mass travels from 0.15 to the equilibrium along that journey, say whether the speed is increasing, whether the acceleration's is that the next question?
It's velocity and then jerk.
It basically, it's the velocity, then acceleration, then the derivation.
Okay, great. So so we're going to do that right now. We're going to do that. And I'm sorry, what we're going to do? Could someone tell me what time is it? Could someone tell me? You'd think I'd be able to tell with the computer.
It's
What's the
3:13.
Okay, thank you. Okay, yes. So we're at least going to fit. Yes. Okay, thank you. I know there's other things we have to do too. But all right, we're going to do that. But I'm going to add one question that should have been added just to make it absolutely clear before we even do velocity or acceleration or jerk. In order to see the pattern, let's add. I'm adding position. Okay. Now, in other words, as the mass goes from 0.15, as the mass travels from x equals 0.15 towards x equals 0, what's happening to the position? And remember, we're being asked to ignore signs. We're just being asked about magnitude. So as obvious as this is, I'm setting this up as a way of seeing the later ones. What's happening to position from 0.15 to 0 is it's clearly decreasing. I mean, it's going from 0.15 to 0, even if you call that negative 0.15. We're only focused on magnitude here, so the answer would still be decreasing. Okay, that's the position. Then we want, what about the magnitude of velocity? In other words, speed. What's happening to the speed? Well, this is now increasing. I'm cutting to the chase just because I know we're running out of time. Also, it looks like with this class, I don't really have to force participation as much, so I really appreciate that. So I'm just going to say that I trust that you'll stop me when I'm not making sense. But if the position was going down from 0.15 to 0, the speed is clearly going up if we just look at our numbers from 0 to 3.87. So the speed is increasing. Okay. Then the acceleration, which to many people may sound like the same question again, but isn't. The acceleration from that endpoint, from that initial point toward the equilibrium, the acceleration is decreasing, right? Because the acceleration was initially something like 30 or some, even if it was negative, it was some quantity like 30 or something. I can't even remember, or 100, it was 100. The acceleration was 100, granted negative 100, but the magnitude was 100. And by the time it got to the equilibrium position, the acceleration had plummeted to 0. So that's a decreasing. So far we have this pattern. And that right there is worth thinking about. I mean, that right there is something still to get used to your whole life in physics, is the very subtle, huge relationship between velocity and acceleration, by virtue of which it really is possible for something to be speeding up while losing acceleration. That's totally what we're saying here, right? I mean, and we've seen things like this before in mechanical physics. Like here's a trick question. I throw something up and it falls back down, like free fall, right? I throw it up and it comes back down. The trick question that I could ask is, what's the acceleration instantaneously at the very top of this trajectory? I'm not actually asking that because, well, if anybody, well, I'm not actually asking because we're getting concerned about time. So, but I'm saying if I throw something up and it falls down at the very top of its trajectory, what is true, what you should believe is that at the top of the trajectory, the instantaneous velocity is 0, right? If you throw something up and it comes back down, because it was having positive velocities, less and less of them, and then it started having negative velocities more and more, so it had to cross through 0 to do that. But if I ask what's the acceleration at the top of some up-down trajectory, at the very tip top, the acceleration is not 0. It had better be 9.8 because it's 9.8 everywhere through that trajectory. It better be 9. This is an analogy, but just to make a point, or it's a side issue to make a point.
Constant, right?
Sorry, what?
I think it's constant, right? The acceleration.
Right, exactly. Like in an up-down thing, in a gravity thing, the acceleration's constant, and it better freaking be. Well, number one, because we believe that, but it better be because if at the top, in other words, when you throw something up at the top, its motion is 0. It does instantaneously cease to move, which is kind of cool. Like something comes fully to rest when it's at the top of an up-down round trip. But it definitely keeps that constant acceleration. What someone just said, it better, because if at the top, if it had 0 speed and also 0 acceleration, then it wouldn't change its speed from 0. So it would just hover forever, right? Like it's actually crazy. People tend to think if something isn't moving, then it can't be accelerating. But if you're not moving and you're not accelerating, then that means if nothing ever changes, then nothing's ever going to change. And you're just stuck in up there. And we never see that. So what I'm trying to say is velocity and acceleration are two independent knobs, two independent parameters that can be tweaked by themselves. And that's what's happening here. As the mass is moving in toward equilibrium, it's gaining velocity, but it's losing acceleration, just to bear that in mind, right? And something similar is going to happen on the other side. Put another way, by the way, you might say it's increasing its kinetic energy and decreasing its potential energy. So now if I ask the next question, which is technically the unfair question, because we don't have any equations or background or something, but if I then say, well, what about the next derivative? What about the rate of change of the rate of change of position? What about the derivative of acceleration, which is technically called jerk, even though it doesn't come up that often? Honestly, offhand, I have no right to ask that. There's no reason offhand that you would have thought about it or have an equation to figure it out or anything. But if you look at the pattern that I just wrote down, right, and it helps that I threw the position in there, but you would have known that even if it wasn't part of the question. If you look at that pattern, what would you guess is the answer to the jerk? Like, I'm saying position is going down, speed is going up, acceleration is going down. What would you guess is happening to the derivative of acceleration? Oh, now I've lost everybody. Wait. Antonio, are you saying something and you're accidentally muted or no? Oh, no? Oh, no, sorry. Go take the lead. No, my fault. Good. Rest of class. Any thoughts on that? I'm saying what's going on with the... Oh, do people just raise their hand? Did you actually just raise your hand, you people? Wow. Or is that from before?
Is it increasing?
I absolutely think so, yes. I think it continues to... Do you believe? I mean, yes. Is that Jessica who just said that? Wait, who just said that? Sorry. Oh, it was Ayeta?
I mean, isn't it because it's changing direction too, that it increases as well?
It depends what you mean. Yes, the fact that it's changing direction is hugely important here, yes. So yes, the only thing I want to be careful of is right now I'm literally... Wait. But
I'm not sure my answer. That's why I stayed quiet. So.
No, I don't. This is my bad. But this is my. So I really just want to say yes because I don't want you to stay quiet. Yes. Hold on. I have to admit something. Sorry. One second. Sorry. But yes, it does matter. It does matter that the thing will eventually, to this whole problem, all these answers are very much affected by the fact that this thing will change direction, eventually come back. very much. Right now, I'm looking at just the first segment of this. I'm just looking at the, you could almost say the first fourth of a period, the section where the thing is just moving in toward equilibrium. And I'm saying a whole bunch of quantities are changing in interesting ways during that simple motion. And I'm saying there's a pattern here. If you look at it, there's a pattern that is correct. Like you can rely on this pattern where as the thing is moving into lower and lower spots, as the thing is moving down, you could say, it's not really down, but moving from 0.15 to 0, I'm saying the rate of its change is going up, but the rate of that change is going down, and the rate of that change is going up. So by pattern, it seems like the rate of that next change is going down, which is true. And it seems like what I'm really getting at is if you see this pattern that's developing, and you think about the fact that this thing is going to go back and forth in positions all the time, like someone just said, it actually would seem that any derivative you could think of, any rate of change of motion of this object that you could imagine, even if you didn't want to solve for it or you didn't know why you'd care, but any one you can think of must be going up or going down based on this pattern, like it's going increasing, decreasing, increasing. So none of the derivatives is zero, which means something really interesting really is happening. This is where differential equations and all that crap is about to come in. Like what I'm saying is that when something, what I'm saying is there's actually, this is a simple motion, it's just back and forth, but there's something mathematical about it that's actually more complex than anything we did in physics 1. And maybe you've done in other math classes. I'm saying when something's in free fall, it falls down, so its positions change. It's got speed. It falls down, so its positions change. It therefore has speed. But as it's falling, as we've seen in other contexts, as something's free falling, its speeds change as well, like it gets faster and faster. So something falling has acceleration. But the buck stops there, right? Like at a certain point, there's a change, but there's no change in the change. The rate of change of the jerk of a falling object is 0, meaning that the acceleration is always one number. And that's why we can make sense of falling objects. We're always in physics looking for some quantity that doesn't change that will allow us to solve for all the things that are changing. Here, what's weird, what seems to be happening is we got something going back and forth, very nice and simple. But if we think about it, that means as it's moving, it's changing its position and therefore has speed, but it's changing its speed, therefore has acceleration. But it seems like from this pattern, it has an acceleration that's changing, which is to say a jerk. But it seems from this pattern that the jerk is changing. So it has a next derivative, which technically is called a whip, but who cares? But by the pattern, that whip is not 0, it's decreasing or increasing. So then it has a rate of, in other words, it seems like something that goes back and forth on a spring moves in a manner that you could call infinitely differentiable. No matter what derivative you pick to describe the motion of this particle, any derivative you pick will never boil down to 0, will never therefore give you some other kinematic property that's constant. And it means that there's an aspect to this motion there's a way in which this motion has no constancy to it at all, thereby making it somewhat of a puzzle. In sum, what I'm saying is this: the jerk, I'm saying, just by looking at this pattern, it seems fair to infer that the jerk is increasing, which is to say, not 0. And from the pattern, it seems reasonable to infer that the next derivative would be decreasing, also not 0. And by jerk, technically what I mean is d2, I'm sorry, no I don't. I mean d4x over dt. No, I don't mean that either. I mean d3x over dt3. And by whip, I mean d4x over d. I'm saying something is moving back and forth. If we look at it for a while, first we realize it won't have a constant acceleration, so we can't use really Newton's laws. We can't use kinematics to get too far in making predictions. We have to go to energy conservation. Then we look at energy conservation a little bit, and we start to realize, you know what? There's a lot that's not constant about this. Like any derivative we think of is not constant. So if anybody were to bring up this, and this is, I know we're almost out of time. We're almost at the end of the question. I believe the final question then comes. I mean, I think we're up to the last question. Is it question 9? Am I right that the very next question is, at what position will we find the mass when t equals 1? Are we up to that question?
Yeah.
Okay, and is that question 9? Is that correct?
Yeah.
Okay, thank you. All right, so question 9, which is really what this is all about. This is now starts the class, okay? This last question is really where this new material begins for us. All up to this was supposed to be getting us there, for good or for bad, okay? But all that technically was old material. Here now we say at t equals 1 second, what is x? What is x? And this question should be the most simple, straightforward, fair question that could be asked of any physical system, because it is the ultimate only physics question. All physics questions are, in the end, given some point of mass at some point in time, what point of space do we expect to find it? Or the reverse, given some point of mass, at what time will we find it at some point in space? Everything in physics is where will it be when, or when will it be where? Like, that's all there is to physics. So it should be totally fair, given some system, to say, all right, in 1 second, like, where will the damn thing be? Like, that's the point of physics. Not only that, we should really be able to ask that of something that seems very repetitive and simple like this. We got a mass, it's going back and forth the same way forever. So we should totally be able to just say at t, what is x? But the fact is, all the work we just did is actually meant to demonstrate that actually, with what we have right now, as facts for this problem and as fundamental principles of physics, what we have right now, this is a surprisingly tricky question to answer. Like, I'm totally pleased if anybody did go into the book or on the web, but the fact is they had to, right? Like, this is a very simple question with not a simple solution. It's like saying, like, is there a God? I mean, yeah, it's a simple question. It doesn't mean, it doesn't start a whole huge discussion. So how do we do this? Like, normally, right? Normally we might say something like x equals 1 f at squared plus v naught t, but we've already established here that a is not a constant. That makes our life difficult. Also, now we're establishing that, like, the derivative of a is not a constant, et cetera, et cetera. So what the heck do we do? What we actually have to do as physicists is invent more physics. But physics can always be invented from old physics because it all makes sense. I'll shut up. Here's what we do. I'm saying it's never about finding anything that any physicist ever thought of that works. The difference between the genius and us is maybe the genius, Newton or Galileo or whatever, maybe they thought of it on their own before we did, because maybe they were spending a lot of time on it and doing nothing else and throwing out a lot of mistakes they made that we never hear about. But once they figured it out, it must be figure outable. We must believe them because it actually makes sense, which means it actually should make sense. So there's got to be a way. What am I going to do? What time? Okay. And I know we're right. Tell me again. Sorry. What time is it? It's 3. What time is it right now?
3:30.
3:30. And this ends at 3:55, right?
Yeah.
Okay. All right. So we're going to start. I'm going to say here, yes, we're getting into differential equations and all that stuff now. And yes, if you happen to have taken a math class called differential equations, then that's great. Like, you'll be somewhat in a stronger position for this. And maybe you even like it already, or maybe you hate that stuff. So maybe you're in a weaker, I don't know. But I'm not expecting anybody in this room has. We're about to do what we need to do this stuff. We're about to show that it all makes sense, just like the physicists had to do. So anything I mentioned about differential equations or anything like that, we're learning here. I mean, as far as I'm concerned, we're not expected to come in with it. So here we go. What do I know? Well, I know I know. And also, I'm in an exam now, right? You're in it. Like, here's the question where I think most people, if didn't know offhand how to do it, they might have looked it up, they might have given up, who knows, who knows. But if you're in an exam right now and you finally get to that last question, that's the hard one. And it's, you know, all the other ones were meant to build to it. Like, what do you do if you really don't know? What do you got to know what to do when you don't know what to do? Well, the first big trick when you're trying to figure something out is, again, don't try to write something relevant and then make it true. Unconsciously, that's what everybody does on science exams all the time. They try to think about what the question's probably looking for, or how this relates to what you study or something, and they try to write down what they think the question's getting at, and then they try to contort it until they get something that seems reasonable. Don't do that. Like, don't try to psych out the question in that way. Always start with something that you know is definitely true, because it's a triple equal sign, or it's a law, or it's universal. Write down something that's definitely true, and then make it more and more relevant to the problem by plugging in numbers for letters, etc. But if you start with what's true and then go to what's relevant, first of all, you get a lot of points along the way because everything you're saying is right. But second of all, you'll start seeing things that you can't see if you assume you know the answer from the start, if you assume you must know the answer from the start. So I'm saying I always start with something that is always true and almost always relevant. Either write it that way or write it this way. And strictly speaking, I should really put arrows because it's really a vector equation. I'm going to say that, right? And I'm going to say in this case, okay, what I know, I also know something else that's true in this. Like, I know if I were in a test right now, I would write that down. Think of it as a stall technique if you like, but when in doubt, write that down. Then when in doubt, write something like this, because this is also totally true. And of course it's relevant, but I mean, true. There's no way you can get points taken off for writing either of those. Now I start putting them together, like I'm saying this, right? And it's not saying that this is all double equal sign now. I'm not saying that the net force is defined as the spring force. I'm saying net force means the sum of all forces, and there's only one force here horizontally, and that's the spring force. So, okay, so I've got this. So this is what I know so far from physics. But but I'm looking to relate X to T. Oh, sorry, I should remind myself of the question. The question is, at T equals 1, what's X? And a really better way to put that in the mindset that I'm encouraging, yes, the question really is, at T equals 1, what is X? But really, that's the 1 is what I'm going to put in at the last possible minute. What I'm really being asked here is, what is X as a function of T? That's what I'm really trying to find, right? How is X related to time? And in this situation that we've now so thoroughly analyzed, except yet somehow never once seen any reference to time. What we're looking for here is, how does position depend on time? And all we know so far is this. That mentions position, but it doesn't mention time. So somehow we got to bring time into here. And yeah, thinking in terms of the best way to bring time in is to think of definitions that are always true and rates of change. That is, I know that by definition, instantaneous acceleration means the second derivative of position with respect to time, right? Like, in general, what I mean by acceleration is the rate of change of position with respect to time, well, instantaneously. So that's what acceleration means, instantaneously. So I can sub that in. So far, physics-wise, if I'm looking for X as a function of T, I have this, right, so far. And here's where, like, this work you have to put down to get this right. Like, even if you found on the web how to do this, like, the web would say this. Like, anything we're about to do with differential equations doesn't make sense unless it makes sense. So if I know what I'm doing, I'm writing these steps down. If I don't know what I'm doing, I'm writing these steps down because they have the only prayer of getting me towards something that means something. I'm now going to rearrange just to make this look a little bit neater. Like, what I have now is, Sorry, two people have their hands up. Is that because if you have a question, please just ask it. But if your hands are still from before, then I apologize, or please put them down. So I have this now. And this is a big deal. Like, and this was just from things that I know, just rearranging things that I already know. But this equation is on the road to something very helpful because here it is, something that has an X in it, something that has a T in it, and something that everything else it has in it may look intimidating, but everything else is just a thinly disguised number, right? Like it wouldn't look as intimidating if they were numbers, but K and M in effect are just numbers in the sense that they are constants. Like I'm not actually writing them as numbers because everything I'm about to say is going to be true, whether K is 200 or 400. Like I don't care about the details of the actual spring, but what I do care is that those details won't change throughout the use of a spring. So K and M are just constants, and X and T are the variables in this equation. They're the only variables in this equation, X and T. I mean, this is the same X here. So I have something that is good, is what I want. I wanted X as a function of T, and that's what's going on here. So good, but the problem is this is almost like too good, too heavy. What I do want how X and T are related, but I want something like I want like that equation I just wrote down is a correct equation. It's not the answer to this. It totally does not apply here. We've said that a couple of times already. Like it won't be the answer here, but it's an example of the kind of thing I'm looking for. I'm looking for a function where the independent variable is like on the right side of the equation and a bunch of things are done to it, all of which produce a dependent variable isolated by itself on the left-hand side. I want to know what must happen to the independent variable in order to generate the dependent variable. And that's what I don't yet quite have. What I have is something far more complex. I have a statement that says how the rate of change of that variable, of one variable, depends on some variable. That's not as directly helpful. I need to unpack this thing and get it in the form of a direct function. This thing, strictly speaking, is called a differential equation. We need to unpack it. We need to do it the way physicists do. So we're going to learn it here together. Like, again, I'm not expecting that anybody knows it already, but I need you to see what the issue is. And I know I can't find my 340. Okay, 15 minutes. In short, we want a function, but we have an integral. In effect, no, I'm just kidding. I'm totally kidding. We want a function, but we have some kind of derivative. So the question is what to do. Many of you may be correctly thinking, well, if you had a function and you wanted the derivative, I'd say take the derivative. But if you want the function and you already have just a derivative, then go backwards, go the other way, Yaverbaum, and integrate. Even though I hate integrating, that's probably what you have to do, Yaverbaum. And that is half true. That is half true. There's something even more subtle than that going on here. And we have to do something more than integration is what I'm trying to say. And tonight's homework is hopefully going to help you see the ins and outs of this. I'm making a quick decision of how much to do of this right now. Okay, to cut straight to the chase, you're gonna practice a lot with homework tonight. And we're going to pick up from here tomorrow. So I'm not trying to give this short shrift. I'm just trying to stay within. I want to say this. I'm going to give the answer first right now partly because, yeah, it's findable on the web anyway. I want to give people satisfaction to make so they can know if they're right or not. I'm going to say the answer now, but it's unusual. I want to make it clear that I'm going to say the answer, and I don't think that by saying it in any way I've explained it. Like, I'm going to explain it after. Yeah, so I'm going to explain it after, but I want you to. What am I trying to say? Hold on a second.
Divide K by M.
Well, oh, okay. Oh, sorry. Yes, sorry. Yes, good point. I was just doing that to see if you were paying attention. No, I was not. That was a legitimate error. Thank you. Yeah, there's an M in there. Let me put it this way. One of the reasons I'm going to give you the answer now, and then we're going to spend a few days talking about how I got it. Not a few days, I mean, but a lot of time tomorrow talking about how I got it. The reason I'm going to do it in this funny order is because this is a topic unto itself. And we are about to solve a differential equation, and some of them can be very tricky. There's not just one way to solve all of them or to just nail the whole topic in one go. The one thing about differential equations, though, that's really important to understand right from the start is coming up with a possibly correct answer can be difficult. But once you have a guess, the thing about differential equations is it is always absolutely 100%. You can always find out whether your guess was right or wrong with 100% certainty. That is, it's hard to come up with the guess, but checking it is a straightforward matter. And therefore, in a way, the way we all do differential equations, in a way, is a highly sophisticated version of guess and check. We are going to do a guess and check thing here. And I'm going to give you the correct guess first so that I'm not wasting your time. But I need to show you tomorrow what you do with incorrect guesses or how you come up with correct guesses and stuff like that. What I want to say right here is we're looking for how x depends on t. What's the function? We've already said that some function like 1/2 at squared, which is a function, will not work here because a is constant. Because a is not constant. We need some kind of function of t that will work here under these funny conditions for a. The guess I'm going to make, that really isn't a guess, in fact, is highly supported, highly motivated conjecture, is I'm going to guess that the kind of function we're looking for is a cosine function, or maybe something related like a sine function or something. But I'm going to guess that it's not going to be like a power function or an algebraic function, that it's going to be a cosine function. The biggest reason I'm going to guess that is if I'm you, if I'm us, is because I was in lab, or because I'm in the middle of a lab where I'm looking at springs moving back and forth, and maybe looking at, or even at least thinking about how the spring's position how the spring's position does depend on time. And if you're looking enough at the spring in the lab, whether you actually make graphs or not, you notice that the spring goes back and forth, crossing through zero, reaching minima and maxima in a smooth way, much like a cosine function, right? That doesn't prove that cosine will describe it at all. It doesn't prove anything, but it proves that if you need a place to start and you know that t squared is not going to work because here a is not constant, it then follows that something like t cubed wouldn't work either, because the derivative of a here is not constant, and t to the fourth is not going to work because the derivative of the jerk is not constant. Like, we were going through those pains before to sort of show ourselves, if there's any function that works in the world, it's not going to be a power function, because those all reduce to a zero derivative somewhere. This looks like, especially if we think about it in terms of lab, we've got an object that in time is going back and forth, having, well, that was awfully sloppy, but something going back and forth, and I'll even dare say something going back and forth, starting here, not starting there. I'll erase that immediately. Like, it's the top thing, not the bottom thing, because we've already established that this mass started at a position other than 0. If we had started it at 0, it wouldn't have gone anywhere. So I'm thinking trigonometric functions because they smoothly go back and forth the way this thing does. And I'm specifically thinking cosine because I think that's the one that captures most directly the idea of something starting from a place that other than 0. So I'm guessing. And as a physicist, what guess really means is coming out of the lab, I'm coming up with a model from what I've been playing around with in the lab. I'm guessing cosine. I'm also guessing I'm totally running out of time. Okay, 8 minutes. I'm guessing that our answer is some kind of cosine. And I'm going to go with that guess because I know that once I flesh it out, I'll be able to find out if it's exactly right or exactly wrong. And if it's wrong, at least I'll have something I'll see why and then tweak the guess from there. And honestly, that is the way to do differential equations but just it gets more sophisticated with experience. So I'm guessing that x is some sort of function of the cosine of x. What do I mean by that? Why don't I just write? Sorry. What do I mean by? Why don't I just write x equals cosine t? Well, I'm not just writing this. I'm not just writing that because of units, because of someone's very good question before. Here's where, if I did, was it Jessica or no, Yeta asked about some, or Gabrielle. Anyway, someone asked about units before. Here's a perfect example where if you don't fully know the answer before you start, your chances of getting there are much better if you do track units and think about them as a scientist, not just a mathematician. What I mean by that is you can't take the cosine of a freaking second or a minute or an hour. Time is measured in units. We never take the cosine of time units. We take the cosine of angles or of things measured in radians or degrees or whatever. So something is not, right from the get-go, I can't literally say that this thing is true. There's going to have to be some kind of placeholder unit before the t. I don't know, but there's got to be some kind of term before the t to cancel out the units and make them appropriate. In other words, there's going to have to be something, if this has any chance of working, to go there before the t that has units of radians per second, so that when I multiply it by t, the seconds will cancel out. I'll be left with radians, and then I can take the cosine of it, right? Just for this, if there's any, and by the way, also the reason we have to do guess and check is some differential equations don't even have answers. We don't know going in for a fact that it will. We know from experience that this one will. But if it's going to work at all, there's got to be a term before the t that has these units. That term I don't know anything about yet besides this. So I can call it anything. It's a placeholder. It's an unknown. I'm going to give it a name. You could call it anything. I'm going to call it what they call it on the internet and the books and stuff. So, and there's a reason for it, but I'm calling it omega. Okay, but please understand that's just a name. You could call it Fred. I'm using omega there to represent some unknown thing that must be measured in radians per second, some unknown quantity. And in fact, I'll go a step further, must be in fact a constant, right? If any of this is working at all, it can't be another variable because that's then a whole other, then we've got 3 variables going on. There's got to be some constant term in here that somehow relates to the spring, is measured in those units, and then by God, if that's true, by electron, whatever, if that's true, then there really also has to be some term before the cosine, if you think about it, because cosine is going to spit out numbers. It's not going to automatically spit out distances measured in meters. This whole thing has to be measured in meters. Also, cosine never spits out numbers greater than 1 or less than -1. And no one ever said that springs were couldn't ever stretch more than 1 meter or something like that. So there's got to be something right here that will be measured in units of meters, or technically meters per radians if you like, but meters, so that the whole right side will be in meters and therefore the left. And it's got to be something. Well, what is it? Well, I don't know what to call it yet, but I'll think about this. And I know we're just about done. But what is the cosine of 0? Anybody?
Is it 1?
Awesome. Yes, it is. Yes, it is. Awesome. The cosine, and we'll get back to as to which of those you all should memorize or not. I'll talk to you about tomorrow. But yes, the cosine of 0 is 1. Whether you know it or you looked it up, the cosine of 0 is 1. So that means when t equals 0, right? Oops, sorry. When t equals when t equals 0, the cosine of 0 is 1. So all of that business, the cosine will turn into 1, and I better multiply it by but sorry, the whole thing will become 1, but there's no law that says that the mass has to start at meter number 1 when t equals 0. Like the mass can start wherever it wants at t equals 0. In our case, for example, it started at 0.15. So that's what goes here is the name that I'm going to put here is the initial position. Like this is still my guess. Okay. And I know we're about to wrap up. I'm building a guess here, but I'm showing you how you build it from lab. I guessed that a cosine function would have the right shape. And then, but I know it has to have a couple of constants. In fact, literally, there'll have to be 2 constants going in here because this is the second derivative that we're looking at. But I know that things have to fit here just by units alone. I'm just giving them names. I'm not saying anything about them. I'm just giving them names. But when I think about it enough, I happen to realize in the search for naming one of them, that one of them I really do know about. I know that whatever term goes right before the cosine must literally be a number measured in meters, which literally is the place that the mass is at t equals 0. I mean, I know that because of the way cosines work. So my final guess now, right, as class is about to end, my guess for how to solve this, my guess is this function where this stands for x at t equals 0, which also then will end up being, based on everything we just said in the English of the problem, which will also be the same as the maximum x. And this thing here, omega, it's not a W, it's supposed to be a lowercase omega. And all we know about that right now is that it's some kind of constant measured in radians per second, okay? With this in mind, this is my guess as to what the function is. And if it's right, you would just plug in 1 for t and solve for x, right? I mean, and if you know how to get omega, you would just plug in and you get your answer. But you don't know that it's right and you don't know how to get omega and it's 354. But before your homework tonight, I'm going to post the homework right after this. I'm sorry, by the way. I'll post the homework. It'll be like yesterday. Or if you want to stay for a couple minutes to figure out how to submit yesterday's, you can do that, blah, blah, blah. But your first thing you're going to do tonight before you start any new homework is you're going to check that I'm right. You're going to check that this is right. How are you going to check? You're going to take the derivative of both sides twice. Like differentiate both. So this is literally the beginning of your homework tonight, so you can see what's going on. Take the derivative both sides twice. Well, it's stupid. I don't have to say both sides, but differentiate twice to get an expression for dx dt. And if somehow you get back, if ever you get your expression back, if your expression ends up looking like that, then you know you're right, Because that's the original condition, that's the original differential equation of the whole problem. Like we're looking for an x such that differentiating it twice in time gets us this. So if the expression I just wrote down, if you differentiate it twice and you get this, you know it's right. If, however, you get something, and you will, if you get something that looks more like this, say you get something that looks like this, you might say, what's that got to do with anything? But if you get something that looks like this, it still means you're right, because K and M were always constants, omega is a constant. We're looking for an expression that captures the relationship among the variables. If you differentiate twice and you get this, well, then that just means, so I'll say if you get that, and you will, okay? But if you get that, then what that means is 2 things. One, it means we're right. That means, 1, check. Like, it means that this is the solution, and you can use it. But it also means, if you get that, it means that that is right, that our cosine thing is right if and only if by omega, that name that we made up, that we don't know anything about it except for 2 units, that constant omega, it simply is just a different name for the square root of k over m, right? If omega is the same thing as k over m, then these two expressions are identical, and we did solve. And I'm telling you all this is true. Like this, you'll just go through these steps tonight, a couple steps, just so you see what I'm saying. But I'm not leading you down like the devil path. I made a guess, and I can check that the guess is right because when I differentiate it twice, I get what I'm supposed to get, assuming that all the different letters here are just different names for the same constant. That's what you will get. And then once you say that, if you know if x equals cosine omega t, and if you know that omega equals the square root of k, and all this is what the textbook's saying, what the web says and all that, if you know those two things, then you can solve the last question numerically and actually get a numerical answer. So I'm saying, and I'm going to leave that for the moment, like the first thing you're going to do tonight on your homework is just get the final answer to this thing if you haven't already, based on what I'm doing. Okay, the portal isn't open yet, but I'll open in a few minutes. And then there's more homework than that. But we're going to pick up from here tomorrow, from right here. Soon part of your homework will include watching lectures of mine to clarify this stuff and to save us time, but not yet. I know people have to go. I'm going to stay for a couple minutes to straighten out any difficulties with anybody. I also have official office hours. I forget when that's not right now, but I'll stay for a couple minutes for anybody who needs anything. But if you're good and you understand this, then look out for the homework, which will be posted fairly soon. And don't, by the way, if the homework gets posted later than you can tonight, if I post it later than is reasonable for you, again, don't stress it. We're all like, just know what it is and bring it with you tomorrow, blah, blah, blah. Like, we're not worried about the clock yet. We're worried about just everybody being together. So I'll try to get that homework to you as quickly as possible. But if you have to go now, go. If you want to stay for a couple minutes and get Google Classroom things straightened out or whatever, then please do.
I have a question, Professor.
Yes. But wait, sorry. But before she asks that question, wait, pause for one. I totally want to answer a question, but I want everybody else to leave who has to, like, don't think you have to be polite to me answering this. Like, if you need to go right now. Okay, go.
Can you just clarify how you solve that omega is radical k over m?
Yes, I can now do that more slowly. Yes, and this is okay. And this is for anybody who's still hanging out. I'm now going to do. Yes, I'm going to do that, and it's sort of the thing I'm asking everybody to do tonight, right before as I start the homework, so they'll see it for themselves. Because I knew I was running out of time. But yes, here's what I'm saying.
Excuse me. Hello?
Oh, sorry, yeah.
Just have to leave, so I just need something. Is the writing on the board, we gonna find it again? Or
oh yeah. All this whole class. Sorry, yeah, you weren't here. I'll put it in the chat right now. All of this stuff you find at. Hold on, sorry. Okay, I just put it in the chat. Every one of these classes gets recorded, and then I'll post the videos at that website that I just. All of this will be posted. Does that make sense or no? Do you see what I'm?
Yes, and Google Classroom.
Oh, but I mean, if you literally. No, I should put it in there. I'll try to put it in there too. But I'm just saying, if you go on the web to jjphysics.com, it's like every lecture that I do, I'm recording, and then I put on this Vimeo site here. So it's not even Google Classroom. It's just a thing on the web that has all of our. Am I making?
Okay, but I don't have the link to it. Can you post it in the?
I just put it in the chat right here. I just put that link. I'll put it in Google Classroom too. But
okay, please put it in Google Classroom. Thank you so much. Okay, bye. Thank you.
Okay.
Have a nice day. Bye.
Okay. So to anybody else who's still here, that was a fair question. But also I have to say, like this whole lecture that we're doing right now. Yes, recorded. Yes, will be posted, and you can go through slowly later. Just have to warn everybody, it doesn't get posted instantaneously. Like it might not be posted right away. Like I have to go through it and download it and then put it up on Vimeo. It's not an automatic Zoom thing. So everybody bear with me. Like all these lectures you can always go back to, but sometimes you might have to wait a night or something. But anyway, on this thing that I'm solving right now, sorry, I'm saying we guessed, and again, people are leaving, that's good. I'm doing this now for is there any other quick personal question like that I should answer first before, I mean, not personal, but any other logistical thing I should answer first before doing this? All right, I'll do the physics. I'm saying this, we guessed X. Okay, and now we're gonna check if it's right. I'm literally saying, okay, I'm gonna check by, taking the derivative of that. Like I have a function x of t. I think it's the right function, but I don't know. How am I going to find out? I'm going to take the derivative of that function, and the derivative is.
I usually actually do this.
Oops, sorry. Maybe doing this a little bit fast because it's after class, but I could do this more slowly tomorrow. But I'm saying first I took a derivative by knowing that the trigonometric derivatives, like I know the derivative of cosine is negative sine, and I know that I'm using chain rule here also because I'm really taking the derivative of a function, right? It's like cosine of omega t. So I do negative sine, and then the derivative of what's inside, which is omega. So I multiply the whole thing by, I'm speaking too fast, but that's the first derivative of the function using trigonometric derivatives and using chain rule. Now I'm going to take the derivative again. And, I just placed the omega where I did just to make it easier to look at. But it's just a sine multiplied by omega. But now I'm going to take the derivative again because we're looking at second derivatives here because of f equals ma. So I take the derivative again. Well, the derivative of negative cosine the derivative of negative sine that I'm looking at now is negative cosine, right? In other words, the derivative of sine is cosine. So I'm not going to change, I can't get rid of that negative sign, it's still there, but I flip back to a cosine, and we still have to do chain rule again because we still have that omega inside. So I'm saying the second derivative is negative x naught omega squared, and then cosine of omega t, right? So we took one derivative, flopped the cosine to a sine, and introduced a negative. Then we took another derivative, it flips it back to cosine, but the negative is still sitting around, which sort of seems annoying. But now I'm saying multiplication is commutative. Like I can rearrange things, the order of things to make things convenient for me. So I will. I'm saying all this right-hand side is really exactly equal to right? And I'm being sort of careless with my parentheses, but I'm literally saying that x naught times omega squared times cosine of omega t. I mean, I could keep going like this if it makes it. But x naught times omega squared times cosine of something is the same as omega squared times x naught times the cosine of something. And why is that helpful? Well, because I'm going to write it one more time just to make it more neat so you see what I'm doing. This is this. Okay, I have this so far. This is the second derivative. But look, I say to myself, but look, I'll even change colors for heaven's sake. This whole business right here, this whole thing, x naught times cosine of omega t, that was my x guess right from the start, right? If I guessed, I'm looking for x. I'm looking for x as a function of t. I guessed that x was x naught times cosine of omega t. Like that's the function I guessed. And if I guess that and carry it through, it appears to be the case that the second derivative of that guess gets me, in other words, it seems like if I work with that guess, then the second derivative of it is negative omega squared x, because I got all this garbage here. I got this long expression, but all this was just without that. All of that was what I was calling x right from the start. So I substitute x for all of that. I realize, in other words, that if you guess what we guessed, you find out that differentiating x twice gets you back to the same original function, but just multiplied by a constant and multiplied by a negative sign. And that's what we've been looking for the whole time. What this thing, in other words, and I'm going to stop right now because I know I'm way over it. Well, I mean, we're after. Like this whole time, we've been trying to solve this. What that really means in English is we're looking for a function for which it's the case that when you differentiate it twice, you get back itself times a constant times a negative sign. Let me say that. Like we're looking for something where if you differentiate it twice, you get back itself times a constant times a negative sign. That is what we got. That's what cosine does. Cosine, you differentiate it once, you get negative sign. You differentiate it again, you get negative cosine, which technically is cosine times -1. We wanted some function that would do that. We wanted an x such that negative k over m times it is exactly what you get when you differentiate it twice. I'm saying a lot, we're going to go over this more, but that, sorry. So we just got dx2, we got this thing up here. We've been looking for something that solves this. I'm saying we're done then. If we were looking to solve this, and if we remember that k over m is just some constant, and we got, instead, we just proved, I think, this, then everything we've been saying is one and the same. It's all just different letters for the same thing, as long as these two, as long as k over m means the same thing as omega squared. That's where I got omega squared must equal k over m. They must just be two different ways of looking at the same number. Am I making it, did I?
Yeah,
work it out?
that completely clarifies everything.
Oh,
thank you.
Thank you for saying, if you say completely, I'll take, that's great. I'm going to retire right now. Thank you. No, I believe you. Good. All right, cool. Anybody, and again, we're going to keep going like this. Like, I hope, I will, I think any other questions? Sorry, any other questions?
From this, we can assume that w equals the square root of k over m.
Well, I'm arguing that we just proved that. I don't think we can assume it, but I think we just proved it.
Okay, and then the first derivative we took would technically be the velocity, and then the
Yes.
second would be the acceleration.
Yes, that's awesome too. Oh, I really, yes, yes, awesome, yes. Any other else? I'm so afraid. I'm afraid to get more questions because I'm afraid to like end on not on a perfect street. But no. Any other questions? Other questions? Any?
So for the homework that we just did, could we have technically redone like a majority of the questions using these new derivations that we just came up with?
That's a really good question. You could have done some of them, a couple of them, but honestly, that's a great question. Honestly, I think it's kind of the reverse, that most of what we just did is only possible if we believe all the stuff that we, like historically, this came after energy conservation and Newton and all that. Like, I think this is possible to do because we believe that. But you're right still, though, that some of those questions would be more quickly answered now that we've done this. Yeah. And like future homework, then you'll just cut straight to the chase then. So yeah, if that makes sense.
Yeah. So now if we resubmit the first homework based off of what we did today, would we not be eligible to get the full 50 points?
No, you would. No, that's also a very fair question, especially with this one, where if you, anybody who literally resubmitted this with all the work that we just did together, I mean, obviously you want to do something to show that you get it, like do it in your handwriting, anything more that you can do to show that it's in your language is great. But yes, if you now resubmitted this from everything we just did, I would still give you 100 because now because even if you think you just got this from my board, it showed both that you've corrected your homework and that you totally paid attention in class. So why would I not? So yes, you could, in the future, it'll be a little trickier to do that because because sometimes the timing will be harder for you to do that. Like you'll have more work, but yes. If you resubmit now with everything we just did, you will get a 50 and that will not be cheating. It just means you're really being a student. Yeah. Does everybody hear? You all got that? And so please do. Yeah. As for the next homework, it's not posted yet. So there's nothing anybody can do until I post it. If I end up posting it later than you have time to do, then that'll be on me. Don't blah, blah, blah. But any other questions?
So just verifying what you want us to do tonight is basically just go through like in our own handwriting what we just did right now, sort of differentiation.
Well, that part was, I did want everybody to do that as the first thing for their homework, but you just did it with me, so it's cool. Like but I didn't mean to suggest that's all of you. There's an official homework too that I just haven't posted yet that comes after this. So that's the main homework that you'll do, and I'll post it in a few minutes. This thing, yeah, I wanted you to start your homework off by doing this. And yes, I guess, right, if you can ideally just copy from your notes into your homework that would be great. I didn't realize I was going to end up doing it right. But yes, that's what I was talking about, this bit that we just did, yes.
And also, if these wind up being like the correct equations, which I think they are, would we know the derivations each time we use them, or would these be?
Oh, that's another great question. Great question. From here on in, once it's true, once we have this established, because you're right, it is true, then from here on in, you can just use the results of it, especially if you understand them. Whenever we have a homework question or an exam question, you can just use the results and you don't have to rederive, except that sometimes I will literally ask on an exam, like I will make a question where I say, show this derivation. Like you are responsible for knowing how to derive. I just don't want you to go through that every time needlessly. But there is a point on the exam where I ask you to do the derivation, just, directly to show that you get it. And so for that you need, so you do need to understand why this works, but no, you don't have to show it every single time we use it, no.
And for the derivation, yeah, I'm sorry, I'm asking a lot of questions. And this derivation, would it be safe for us to say, using like how you wrote out, guess that x equals f cosine t, or are you going to show us a more in-depth of how?
Oh, no, that's totally, yeah. I mean, I am going to say more about it, but in the end of the day, there is literally no way it all starts with some kind of a guess. It's just a question of how educated the guess is. So yes, that is fully legitimate to say that. Because you check the guess. Like guess and check is always legit in physics and math as long as there's a check. Like if there's no check, then it is just wild guessing. But no, yeah, that's sufficient to say. Any other or is it? And by the way, all these questions are good. You don't have to apologize. I mean, I appreciate them all. But any other? Okay. All right, I'm going to sign off now. Again, the homework will be posted shortly in a second, I hope. And there will be office hours and stuff. I think they're in the syllabus, but I think they're in the morning. But anyway, I'm going to go now if that's cool with everybody. All right.
One last question.
Oh, yes.
Google Classroom, would you be able to like see our old submissions and be able to open them, the PDFs, or do you want us, like if we resubmit it, to also resubmit the first trial? Like, let's say I still have the PDF saved on my computer for the first attempt. Should I be like relabel the title of it as like attempt 1 and then attempt 2 as my second PDF?
That would be the absolute ideal. I would love, yes, if you could do that, that would be great. And that would be the best. Yes. Thank you. Awesome. Other people who are still here, are you guys waiting to, does anybody need to ask a personal question that or are you just waiting? Like Madeline or Shian, are you guys good, or do you need?
Yeah, I just wanted to see that derivation because I was confused, and that was very helpful.
Awesome. All right, good. I love very helpful. Could you write that on my tombstone, please? No, good. Okay. And same thing with, and also, wait, Shian, I know you.
I have that. Thank you. It was really helpful.
I'm not just fishing for thanks, but okay, cool. All right, good. All right. And by the way, also weird note, Aaliyah, wait, I'm saying it wrong. Aaliyah?
Yeah.
Can I say, I'm going to start, the fact that you put a picture up of yourself with you smiling, can I say that is so smart, and I didn't realize it? I'm going to tell other people, I keep thinking that is not a picture, that is you smiling and like loving what's going on. It's such a great trick. I mean, what was that?
I said I'm glad that it's doing good things for you.
Yeah, no, it's totally smart. Everybody should do that. I mean, even if it's a cartoon, it's totally, yeah, it makes me happier. Right, anyway, okay. Cool. So, and I get to the fact that you're smiling in real life all the time is equally helpful. I totally, for real. So, all right, I'm going to go before I get myself in trouble. Thank you, everyone.
All right, thank you.
Thank you. Okay, bye.